Tonight, I want to tell you about an object most people have never heard of, even though it may be the most hostile thing the universe knows how to make. It isn't a black hole. Black holes get all the attention. They show up in the movies. They swallow light. Everyone already half understands them. The thing I mean is quieter and far less famous. It's a dead star called a magnetar, and the danger it carries has nothing to do with its gravity. Wrapped around it is a magnetic field so violent it can reach across thousands of light years and pull at the atoms inside your body. A black hole waits for you to fall in. A magnetar reaches out. On the 27th of December, 2004, the most luminous event ever recorded from beyond the solar system reached the Earth. Spacecraft from low Earth orbit out to the edge of the planetary system had spent years recording the steady background level of the high-energy sky. Within about 0.2 of a second, the gamma-ray and X-ray detectors aboard them did not merely spike, they saturated, driven past the highest value they were built to register, the way a kitchen scale gives out the instant you set a truck on it. For that fraction of a second, the radiation flux arriving at Earth from one point in the sky exceeded that of the full moon, almost all of it in gamma rays and hard X-rays far outside the range of human vision. Several instruments recorded it not directly but as a reflection off the surface of the moon. The first candidate was the sun, the ordinary source of anything sudden in the high-energy sky. Both the timing and the arrival direction excluded it. By cross-correlating the exact moment the wavefront struck spacecraft at different positions, a technique called timing triangulation, the source could be pinned down since a sheet of radiation sweeps over separated detectors at slightly different instants. The offsets converged on a point toward the inner Milky Way, on the far side of the galactic center from us, roughly 50,000 light-years away. The object there belonged to a class known as soft gamma repeaters, neutron stars that throw off irregular bursts of low-energy gamma rays. This one had been bursting on and off for years, and in the preceding months its activity had climbed sharply. A magnetar. The flare was not a single pulse. A hard initial spike lasting about 0.2 of a second gave way to a fading tail that lasted roughly 6 minutes, and that tail rose and fell on a fixed cycle once every 7.5 seconds. That period was the rotation of the neutron star. As it turned, a radiating region on and just above its surface swept across our line of sight, modulating the signal. The tail itself came from a trapped fireball, a confined cloud of electrons, their antimatter counterparts, and photons held against the star by closed magnetic field lines and radiating as it slowly cooled and shrank. Carried inside that decaying signal was the spin rate of the star as it had been 50,000 years before the light arrived. That figure matters more as a span of time than of distance. The radiation left its source about 50,000 years ago. At that point, there were no cities, no agriculture, no writing. Modern humans were living through the last glacial period, alongside now extinct megafauna. The wavefront traversed 50,000 years of interstellar space, while the entire length of recorded history occurred somewhere along its line of travel, and it reached us in the final days of 2004. Its path was far from empty. The magnetar lies inside a dense cluster of very massive young stars near the galactic center, a region thick with gas and dust. Ordinary visible light from that part of the galaxy is heavily absorbed before it can reach us, which is why the region is dim or invisible to optical telescopes. Gamma rays and hard X-rays slip through that same dust with little loss, so the flare arrived with its energy largely intact, even though the ordinary starlight around its source is screened from view. What crossed the gap was electromagnetic radiation at the extreme high end of the spectrum, individual photons each carrying hundreds of thousands to millions of electron volts, hundreds of thousands of times the energy of a single photon of visible light. Higher photon energy means deeper penetration. and these were energetic enough to reshape the chemistry of a planetary atmosphere from across the galaxy. Earth generates its own magnetic field in the convecting liquid iron of its outer core, and that field carves a cavity in space, the magnetosphere, that deflects the charged particles of the solar wind. On the sunward side, it normally reaches tens of thousands of miles out before solar wind pressure balances it. The flare delivered enough energy to compress that cavity inward for the length of its brightest phase. The magnetic boundary of an entire planet was pushed back by a stellar remnant 50,000 light-years away. In the upper atmosphere, the same radiation ionized the air, stripping electrons from atoms in the layer where low-frequency radio waves reflect and travel around the curve of the Earth. The level of ionization was comparable to that produced by a large solar flare, even though it came from a single city-sized object on the opposite side of the galaxy. Ground receivers recorded abrupt shifts in how very low-frequency radio signals propagated that night, and several stations logged the same disturbance independently of one another. The dominant energy release occupied about 0.2 of a second. In that interval, the magnetar emitted on the order of the total energy the Sun radiates across 100,000 years, exceeding the only two comparable giant flares recorded before it in 1979 and 1998. By roughly 100 times in its initial spike. That output came from a body you could cross on foot in an afternoon. The radiation that reached Earth was only the prompt emission. At the source, the eruption ejected matter. Over the following days and weeks, radio arrays tracked an expanding cloud of radio-emitting material moving away from the magnetar at a substantial fraction of the speed of light. The event had not only released radiation but also expelled magnetized plasma into the surrounding space, and that outflow was directly imaged as it spread. A neutron star is the densest stable form of matter known, compressed past the density of an atomic nucleus, and this one still expelled part of its outer material in one convulsion. To say the flare was detected suggests a warning, a signal that runs ahead of the effect. No such separation exists. The photons that registered the eruption on our instruments were the same photons that compressed the magnetosphere and ionized the air. Information and effect travel together at the speed of light and arrive at the same instant, because no signal can outrun light. For an event like this, detection is not advance notice. It is the measurement of an arrival that is already complete. The atmosphere absorbed the gamma rays at high altitude, well before they could reach living tissue, and the ionospheric disturbance was the immediate signature of that absorption. The change measured in the upper air was not the damage. It was the byproduct of the shielding that prevented the damage. At 50,000 light-years, the flux had thinned enough that the atmosphere could intercept all of it. The identical flare at close range would be lethal. The distance alone reduced it to a faint perturbation we needed instruments to notice. Every measured effect, the saturated detectors, the compressed magnetosphere, the ionized upper atmosphere, the relativistic plasma flung into space, originated in an object about a dozen miles across, the collapsed core of a star that exploded long ago. The energy behind all of it did not come from the object's mass, and it did not come from its gravity. It came from the rearrangement of its magnetic field. How strong must a magnetic field become for a stellar remnant the width of a small town to reach across the galaxy and physically alter the atmosphere of a planet? You are lying inside a magnetic field at this moment, and you have never once felt it. The Earth produces a field of roughly half a Gauss at its surface, the Gauss being the standard small unit for magnetic strength, where strength is measured by the force the field exerts on moving electric charge. It is generated far below you, in the outer core, where liquid iron convects and carries electric currents, and moving charge is one of the two ways nature makes a magnetic field. That half-Gauss field is enough to turn a compass needle and to steer particles from the sun toward the poles. It is not enough for any nerve in your body to register. As the baseline for everything that follows, hold that number. Half a Gauss. A refrigerator magnet runs to about 50 or 100 Gauss at its face, 100 times the planet's field or more. And it is built by the second mechanism. Its strength comes not from currents in wires, but from the electrons inside the iron itself. Every electron behaves as a tiny magnet, and in most materials their orientations cancel. In a ferromagnet, they lock into alignment across large regions, and the sum of those aligned spins is the pull you feel when it grabs a steel door. Even so, at 100 Gauss, the field does nothing to you. You can press your palm flat against it and feel only the magnet, never the field. The first field, strong enough to be treated as dangerous, sits in a hospital. A clinical MRI scanner runs between about 15 and 30,000 Gauss, 1.5 to 3 Tesla, where 1 Tesla equals 10,000 Gauss. Its coils are superconducting, cooled with liquid helium so current flows through them without resistance. At this strength, a loose steel object becomes a projectile, and a wrench or an oxygen cylinder left in a pocket will accelerate across the room and strike the machine hard enough to kill. Research scanners reach 7 Tesla, 70,000 Gauss, and at that field people report brief vertigo, faint flashes at the edge of vision, and a metallic taste, the field acting on the fluid of the inner ear and on the nerves behind the eye. Should the coil ever fall out of its superconducting state, its stored energy dumps into the helium at once, which boils off in a violent release the operators call a quench. Past medicine. In the laboratory, the numbers climb again. The strongest continuous field ever sustained on Earth is about 45 Tesla, 450,000 Gauss, produced by a hybrid magnet that consumes megawatts of electrical power with water pumped through it fast enough to keep it from melting, and it can be held only in a volume the size of a soda can. A weaker field, around 16 Tesla, 160,000 Gauss, does something that sounds impossible. It lifts a living frog into the air. Water is weakly diamagnetic, repelled rather than attracted by a strong field, and a frog is mostly water, so the gentle push spread through every cell at once balances gravity, and the animal floats in the bore unharmed. Diamagnetism is not special to frogs. Every material is faintly diamagnetic, every object slightly repelled by a strong enough field. Because the field disturbs the electron motion inside every atom, the effect is simply too small to notice until the field becomes enormous. For an instant, we can go far higher. By discharging a bank of capacitors into a small coil, physicists reach about 100 Tesla for a few thousandths of a second without wrecking the equipment. To go beyond that, the coil cannot survive. In explosive flux compression, a magnetic field is crushed into a collapsing space by a chemical charge, and for a few millionths of a second, it reaches something like 25 million Gauss, a couple of thousand Tesla, before the device is destroyed in the same instant it sets the record. Every measurement at that level annihilates the instrument that made it. That is the ceiling of human capability. 25 million Gauss, held for microseconds, paid for with the wreckage of the apparatus, now leave the Earth entirely. An ordinary neutron star, the common remnant of a supernova, carries a surface field of about 1 trillion Gauss, 1 followed by 12 zeros. That is roughly 40,000 times the strongest field we can force out of a self-destroying explosion, and millions of times the strongest we can hold steady. At 1 trillion Gauss, the field stops being a thing that merely acts on objects placed inside it and begins to act on the structure of matter itself, and that shift is where its real danger begins. The field also channels charged particles along its lines and accelerates them to extreme energies, which is part of why neutron stars shine in ways ordinary stars cannot. And a neutron star is not the top of the scale. A magnetar carries a surface field of about 1 quadrillion Gauss, 1 followed by 15 zeros, 1,000 times the field of an ordinary neutron star, and the strongest magnetic field known anywhere in the universe, with nothing else ever measured that comes close. Laid out from end to end, the ladder runs from half a Gauss at the surface of the Earth to a quadrillion Gauss at the surface of a magnetar, 15 factors of 10 apart, the gap between a single footstep and a walk across the width of the observable universe. A question is how anyone claims to know the field of an object a dozen miles wide and 50,000 light-years away, one that emits no steady visible light. The answer comes from its spin. A magnetar rotates, and its rotation slows measurably over time because a turning magnetic field radiates energy and drags on the star like a brake. Measure the rotation period, then measure the rate at which that period lengthens, and the surface field follows from the two together under the model of a spinning magnetic dipole. The 7.5-second beat in the tail of that 2004 flare, and the slow lengthening of periods like it, are the raw numbers from which a quadrillion Gauss is calculated. Because a stronger field breaks the spin harder, magnetars slow quickly by stellar standards, which is one reason their violently active phase is brief rather than permanent. A second, independent check comes from the light itself. In fields this strong, charged particles absorb radiation only at sharply defined energies fixed by the field, leaving features in the X-ray spectrum whose positions encode its strength. Two unrelated methods, the slowing spin and the spectral lines, converge on the same staggering value. One more property of this number governs everything still to come. The energy stored in a magnetic field does not rise in step with its strength. It rises with the square of the strength. Double the field, and you quadruple the energy. Raise the field by a factor of 1,000, the step from a neutron star to a magnetar, and the stored energy rises by a factor of 1,000,000. So the climb up this ladder is far steeper in energy than it appears in field strength, and a magnetar does not stand one rung above a neutron star. In everything the field is able to do, it stands 1,000,000 rungs above it. A field that nudges a compass at half a Gauss, throws a wrench across a room at 15,000, and lifts a frog at 160,000, reaches a quadrillion at the surface of a magnetar. What does a field that strong do to a single atom placed inside it? An ordinary atom holds its shape through a single contest. The positively charged nucleus pulls on the electrons around it, and those electrons, bound by that electric attraction, settle into orbitals whose rounded shapes are fixed by the balance between the pull and the electron's own motion. Those shapes are the entire basis of chemistry. The way one atom bonds to another, the angles between the bonds, the structure of every molecule in your body, all of it follows from the roughly spherical geometry of electron orbits under the electric force. Put that atom in a magnetic field, and a second force enters the contest. A magnetic field bends the path of a moving charge into a circle, and the stronger the field, the tighter the circle. For the electrons inside an atom, the field winds their motion into small loops while the nucleus continues to bind them in their usual orbits. At the fields we know on Earth, the electric pull dominates overwhelmingly, and the magnetic effect is a negligible nudge. There is a specific strength at which the two become comparable, where the magnetic bending energy matches the electric binding energy of the atom, and that threshold is about 2 billion Gauss. Below it, a field only perturbs an atom slightly. Above it, the field, rather than the nucleus, sets the shape of the electron cloud. An ordinary neutron star sits about 400 times above that threshold. A magnetar sits about 400,000 times above it. At those strengths, the contest is not close. The magnetic force dominates completely, and the atom is no longer governed by its own nucleus in the way chemistry assumes. That 2 billion Gauss line is not an arbitrary figure. It is a natural unit of magnetic strength assembled from the electron's charge, its mass, and the constants of quantum mechanics, the field at which the magnetic scale and the atomic scale coincide. It falls out of the same constants that fix the size of an atom in the first place. What happens to the electron is the core of it. Its motion across the field lines is wound into the tightest possible loops, and in quantum terms that motion is no longer continuous. It is quantized into fixed rungs called Landau levels, and the electron is forced onto the lowest rung in the two directions perpendicular to the field. The only direction left for free movement is along the field lines. Two of its three dimensions of motion are frozen out. An electron that once ranged through the full volume around its nucleus is now confined to a narrow channel, free to slide along the field but pinned hard across it. The shape of the atom follows from that. Across the field, the electron is held to a loop far smaller than the normal span of an atom, so the atom is crushed sideways to a fraction of its former width, while its length along the field barely changes. What was a rounded thing becomes a thin needle, aligned with the field lines. In the most extreme cases, hundreds of times longer than it is wide. Every atom at the surface of a magnetar is a slender filament pointing the same way as every other, because one field threads through all of them. The squeeze also changes how tightly the atom holds together. Pressed close to the nucleus across the frozen directions, the electron is bound far more strongly. Hydrogen, which surrenders its electron at about 14 electron volts under normal conditions, holds that electron with hundreds of electron volts of binding in a magnetar field. Matter aligned with the field is far harder to pull apart than the same matter on Earth. These needle atoms are not fragile. They are bound with an energy ordinary chemistry never approaches. The Landau rungs themselves carry enormous energy, and their spacing grows in step with the field. At an ordinary neutron star, the gap is already around 10,000 electron volts, the energy of a medical X-ray. At a magnetar, it climbs into the millions of electron volts, into the gamma-ray range, past even the energy locked inside an electron's own mass, which is about 500,000 electron volts. This is not a remote abstraction. It is the source of the spectral lines that let us measure the field from across the galaxy. A charged particle in the field absorbs radiation only at energies matching the gap between the rungs, cutting a notch in the spectrum at a precise energy set by the field. For magnetars, the lines we actually catch fall in the X-ray band and are attributed to protons rather than electrons, since the electron lines lie far higher, up in the gamma rays, where they are much harder to record. The field strength is imprinted directly on the light the atom absorbs. The frozen geometry has one more consequence. Because electrons slide freely along the field lines but barely move across them, the surface conducts heat and electric charge readily in one direction and resists it in the others. Energy flows along the field and stalls across it, which helps funnel heat into narrow regions and feed the bright, beamed emission we detect from the surface. The deformation of single atoms scales all the way up to how the whole star glows. With the geometry of every atom rewritten, chemistry is rewritten with it. Bonds form along the field lines rather than in the rounded arrangements we know, and atoms link end to end into long chains threaded on the field, like beads forced to lie single file along a wire. Substances that cannot exist on Earth become stable, and substances stable here cannot form at all. Above a field of roughly 10 to 100 trillion Gauss, matter can settle into a condensed phase held together by this field-aligned bonding, a state sometimes called magnetic condensation. The surface of a magnetar may not be gas, and may not be solid in any familiar sense. It may be a sheet of these chained, field-locked filaments, a form of matter found nowhere on Earth, nowhere in any laboratory, and not even on an ordinary neutron star. None of this is pure theory drawn from equations alone. The lowest rungs of it are observed. Magnetic white dwarfs carry fields of millions to billions of Gauss, far weaker than a magnetar but already past the gentle regime, and the light from their atmospheres shows spectral lines shifted, split, and distorted exactly as strong field atomic physics predicts. We have watched real atoms deformed by real fields, then followed the same physics upward by a factor of 1,000,000 toward the surface of a magnetar. The extrapolation is long, but it rests on measured ground. We treat chemistry as a fixed set of rules, the same everywhere, the bedrock under biology and materials and life. It is not fixed. It is simply what happens to matter when the magnetic field is weak, which on Earth it always is. The rounded atom, the bond angles, the entire periodic logic of how substances combine are a local condition. true here and across most of the universe, only because most of the universe carries feeble fields. Raise the field high enough, and matter follows a different set of rules, just as lawful and just as exact, met only in places where nothing could survive to write them down. So the field has reshaped the atom, frozen the electron's motion, and overturned the rules of bonding. That is what it does to matter. The next question reaches past matter altogether. If a field this strong can deform an atom and remake chemistry, what does it do to the empty space between the atoms, to the vacuum we usually treat as nothing at all? Empty space is not empty. In quantum field theory, the vacuum is the lowest energy state of the fields that fill all of space, and that lowest state still fluctuates ceaselessly. Pairs of particles, an electron and its antimatter twin, the positron, continually appear and annihilate, borrowing energy for an interval so brief that the uncertainty principle lets the debt go unpaid. These are called virtual particles. They never settle into permanent existence under ordinary conditions, yet they are not a bookkeeping trick. Their effects are measured. They shift the energy levels of hydrogen by a tiny, calculable amount. They produce a faint attraction between two uncharged metal plates held close together in vacuum. They alter the magnetism of the electron itself, and that alteration has been matched to prediction to about 12 digits. This active vacuum is one of the best tested ideas in all of physics. Bring a magnetic field into that fluctuating vacuum. The virtual electron and positron in each fleeting pair carry opposite charge, so the field pushes them in opposite directions during their brief lifetime. Across countless pairs, this gives the vacuum a slight, organized response to the field, a property called vacuum polarization. Empty space acquires a structure it did not have before, and that structure has a direction, set by the field lines. Space that was identical in every direction becomes different along the field than across it. Light traveling through such a space no longer moves at a single speed. A photon polarized along the field lines travels at a slightly different speed than one polarized across them. The vacuum gains two indices of refraction, one for each orientation, which is the defining behavior of a birefringent material. On Earth, certain crystals do exactly this. A clear slab of calcite laid over a line of text shows two images, slightly offset because the two polarizations of light move through it at different speeds and bend by different amounts. A strong enough magnetic field makes the vacuum itself behave like calcite. Nothingness splits light. This was predicted in 1936 by Werner Heisenberg and Hans Euler, working out the consequences of quantum electrodynamics for fields far beyond anything then achievable. For most of a century, it stayed a calculation with no place to test it, because no field on Earth comes near the strength required. The place to test it was a neutron star. In 2016, astronomers using the Very Large Telescope in Chile measured the polarization of the faint optical light from an isolated neutron star with an extreme magnetic field. The light arrived strongly polarized, aligned in a way that matched the prediction for a vacuum made birefringent by the star's field. And that alignment is hard to produce by any conventional process near the star. It was the first observational evidence that empty space can behave as an optical medium when the field is strong enough. The result is still being refined and rechecked. Birefringence is the mild end of what the field does to the vacuum. As the field grows, the vacuum's response stops being a slight correction and becomes a large one, and the scale where that happens is called the critical field, or the Schwinger field, after Julian Schwinger, who analyzed it in detail, building on the earlier work of Heisenberg, Euler, and Fritz Sauter. Its value is about 44 trillion Gauss. That number ties straight back to the deformed atoms. It is the field at which the spacing between the Landau rungs, the quantized levels of electron motion across the field, grows to equal the energy locked inside an electron's own mass, about 500,000 electron volts. At that point, the magnetic energy available to a single electron is as large as the electron itself, and the line between the field and the particles it acts on begins to blur. A magnetar's field, around 1 quadrillion Gauss, sits roughly 20 times above that critical value. It is one of the only places in the universe where the field is not merely near the threshold at which the vacuum turns strongly nonlinear, but well beyond it. A pure static magnetic field, however strong, does no work on a charge and cannot by itself spark lasting matter out of nothing, the way a strong electric field can. But a magnetar is not a quiet field sitting alone. It is flooded with high-energy photons, and in a field above the critical value, those photons behave in ways forbidden in ordinary space. A single gamma-ray photon crossing the field can split into 2 lower-energy photons, a process that does not occur in field-free vacuum at all. A sufficiently energetic photon can convert directly into a real electron-positron pair in the presence of the field. The vacuum near a magnetar is a nonlinear optical medium in which light splits, bends, and turns into matter, and these processes shape the radiation we receive, softening the high-energy spectrum as the most energetic photons split or convert before they can escape. Quantum electrodynamics is the most precisely verified theory in science. The same framework that predicts vacuum birefringence and the critical field also predicts the electron's magnetism, and that prediction matches experiment to about 12 decimal places, an agreement with no equal anywhere in physics. When that theory states the vacuum becomes birefringent in a strong field and nonlinear above the critical value, there is every reason to trust it. A magnetar is, in effect, a quantum electrodynamics laboratory we could never build, running experiments at field strengths the Earth will never reach and broadcasting the results to us as light. We are used to treating the vacuum as a stage, a passive absence on which events take place. Near a magnetar, it is not a stage but an active medium, with a direction, 2 separate light speeds, and processes in which photons split apart and convert into matter. The deepest strangeness of these objects is not what their fields do to atoms, which is extreme enough on its own. It is that the field reaches past the atoms entirely and changes the properties of nothing, of the empty space that everywhere else behaves like the absence of anything at all. The fabric we treat as the backdrop to reality turns out to be one more thing that bends near a magnetar. Everything seen so far, the deformed atoms, the rewritten chemistry, the altered vacuum, is the field acting on its surroundings, and all of it is powered by the energy held in the field itself. So the next question is the one that turns this from a study of strangeness into a study of danger. How much energy is stored in a field of 1 quadrillion Gauss, and what holds all of it in place? Empty space is not empty, and stranger still, that emptiness has a breaking point. In quantum field theory, the vacuum is the lowest energy state of the fields that fill all of space, and even at its lowest, it never goes still. Pairs of particles, an electron and its antimatter twin, the positron, surface and vanish without pause, borrowing energy for an interval so short that the uncertainty principle lets the debt go unpaid before it is noticed. These are called virtual particles, and they never become permanent under ordinary conditions. Yet they are not a bookkeeping fiction. Their fingerprints are measured. They shift the energy levels inside a hydrogen atom by a tiny, calculable amount that matches experiment. They pull 2 uncharged metal plates together when the plates are held a hair apart in vacuum, a force produced by nothing but the restless field between them. They change the magnetism of the electron itself, and that change agrees with prediction to about 12 digits, the closest match between theory and measurement anywhere in science. There is a deeper unease buried in this. If the vacuum carries energy, the obvious question is how much. And when physicists calculate the energy of empty space from first principles, the answer comes out larger than what the universe actually shows. By a margin so enormous, it is often called the worst prediction in the history of physics. We do not know why the vacuum weighs so little when the theory insists it should weigh so much. The emptiness that fills every cubic inch of the cosmos is, at its foundation, still an unsolved mystery. And it is this barely understood emptiness that a magnetar's field reshapes. Bring a magnetic field into that fluctuating vacuum. The virtual electron and positron in each fleeting pair carry opposite charge, so the field pulls them in opposite directions during their brief existence. Spread across countless pairs, this gives the vacuum an organized lean in response to the field, a property called vacuum polarization. Empty space takes on a structure it did not have, and that structure has a direction, fixed by the field lines. Space that was the same in every direction becomes one thing along the field and another thing across it. Light passing through such a space no longer travels at a single speed. A photon polarized along the field lines moves slightly slower or faster than one polarized across them. The vacuum gains two separate indices of refraction, one for each orientation, which is the exact definition of a birefringent material. The phrase everyone learns, the speed of light in a vacuum, quietly splits in two. On Earth, certain crystals already do this. A clear slab of calcite laid over a printed line shows the text doubled, two images slightly apart, because the two polarizations of light cross the crystal at different speeds and bend by different angles. A strong enough magnetic field turns the vacuum itself into that crystal. Nothingness splits light. This was worked out in 1936 by Werner Heisenberg and Hans Euler, who followed quantum electrodynamics into fields far beyond anything achievable then. For most of a century, it stayed a calculation with nowhere to be tested, because no field on Earth comes within a vast distance of the strength required. What makes it stranger is how far the effect reaches. The birefringent region does not cling to the surface. It extends outward for a great distance around a magnetar, and as light climbs away from the star and threads through that zone, the vacuum gradually aligns the light's polarization, locking it into a single orientation long before it escapes. By the time the light reaches us, it carries a polarization stamped not by the surface, but by the empty space high above it. Reading that light, we are reading the signature of nothing behaving like something, written across thousands of miles of vacuum, and from it we can begin to deduce the geometry of the field that did the writing. The place this was finally tested was a neutron star. In 2016, astronomers using the Very Large Telescope in Chile measured the polarization of the faint visible light from an isolated neutron star with an extreme field. The light arrived strongly polarized, aligned in just the way the birefringent vacuum prediction required, and hard to explain by any ordinary process near the star. It was the first observational evidence that empty space can act as an optical medium when the field is strong enough. The result is still being rechecked. The field treats the two polarizations of light differently in another way as well. When a photon splits into two inside a strong field, only one of the two polarizations is permitted to split, while the other is forbidden by the rules of the process. The vacuum near a magnetar therefore filters the light that crosses it, draining energy out of one polarization and not the other, reshaping the spectrum by a selection rule with no counterpart in empty space anywhere else. Birefringence is the gentle end of what the field does to the vacuum. The violent end is a threshold. As the field climbs, the vacuum's response stops being a faint correction and becomes a dominant one, and the scale where that crossover sits is called the critical field or the Schwinger field, after Julian Schwinger, who analyzed it in depth, building on Heisenberg, Euler, and Fritz Sauter. Its value is about 44 trillion Gauss. That number ties straight back to the deformed atom. It is the field at which the spacing between Landau rungs, the quantized steps of electron motion across the field, grows to match the entire energy locked inside an electron's own mass, about 500,000 electron volts. At and above this point, the magnetic energy handed to a single electron is as large as the electron itself, and the boundary between the field and the particles it governs begins to dissolve. For an electric field at this same critical strength, The consequence is dramatic and fully understood. The field feeds the virtual pairs enough energy that they no longer have to vanish. They are pulled apart and made real, and the vacuum sparks into a shower of genuine electrons and positrons. The way air struck by enough voltage breaks down into a bolt of lightning. The vacuum has, in effect, a breakdown voltage, a strength beyond which it can no longer remain empty space. A spark in air is matter rearranging itself. A spark in the vacuum is matter arriving. Electrons and positrons that did not exist an instant before, called into being by the field alone. The same threshold also marks where the two speeds of light in the vacuum pull far enough apart to matter, so that one polarization lags the other by a measurable amount over the distances around the star, which is part of what observers are hunting for in the light. A magnetar's field, near 1 quadrillion Gauss, stands roughly 20 times above that critical value, among the strongest fields anywhere since the first moments after the Big Bang. Here the popular image overshoots, and the truth needs care. A pure, unchanging magnetic field does no work on a charge and cannot by itself tear lasting matter out of the vacuum the way an electric field can. But a magnetar is not a still field standing alone. It is drowning in high-energy photons, and above the critical value, those photons behave in ways forbidden in ordinary space. A single gamma-ray photon crossing the field can split into two. A sufficiently energetic photon can convert outright into a real electron-positron pair. The vacuum around a magnetar becomes a nonlinear medium in which light bends, splits, and condenses into matter, and these conversions shape the radiation that escapes, draining the highest energies away before they can leave. The reason to believe in any of these is based on the evidence supporting the theory behind it. Quantum electrodynamics is the most precisely confirmed theory in all of science, the one whose prediction for the electron's magnetism matches measurement to 12 decimal places. When that same theory says the vacuum turns birefringent in a strong field and nonlinear past the critical one, there is every reason to trust it, and there is something fitting in where the proof comes from. We cannot build fields like these, so the experiment is beyond us. It runs only where fields this strong actually occur, and the result reaches us across the galaxy as a single thread of polarized light. We are used to treating the vacuum as a stage, a passive nothing on which events happen. Near a magnetar, it is not a stage. It has a direction, 2 speeds of light, a selection rule for which photons may split, and a strength beyond which it can no longer stay empty. The deepest strangeness of these objects is not what they do to atoms, extreme as that is. It is that the field reaches past matter entirely and alters the properties of nothing, the one thing we assumed had no properties to alter. The emptiness we have never managed to explain turns out to bend, split, and break near a dead star a dozen miles wide. Everything so far, the deformed atoms, the rewritten chemistry, the altered and breakable vacuum, is the field pressing on the world around it, and all of it is paid for by the energy held in the field itself. So the next question is the one that turns this from a study of strangeness into a study of danger. How much energy is stored inside a field of 1 quadrillion Gauss, and what holds all of it in place? One fact governs everything that follows. The energy stored in a magnetic field does not climb in step with the field's strength. It climbs with the square of it. A magnetar's field runs about 1,000 times stronger than an ordinary neutron star's, so it holds close to 1,000,000 times more energy. Carry the full calculation through for a field of 1 quadrillion Gauss threaded across an object a dozen miles wide, and the total lands on the order of the energy the sun radiates in 1,000,000 years. The sun fuses 600 million tons of hydrogen into helium every second, and has done so for over 4 billion years. Take everything it will radiate across 1,000,000 years, the full output of the star that feeds all life on Earth, sustained for a span 200 times longer than our species has existed, and fold all of it into one dead object you could stroll across in an afternoon. Everything human civilization has ever generated, every power plant and engine and fire across all of history, would not make a dent against it. And nothing is being produced there. There is no fusion, no fuel, no furnace burning. The energy is simply held, already present, stored in the shape of the field itself. The largest flare a magnetar has ever shown us spent only a fraction of this reserve, which is why a single magnetar can erupt again and again across its life without draining the account. There is a stranger way to weigh it. Energy and mass are the same quantity in two forms, bound together by the speed of light, so a concentration of energy this extreme has a weight of its own. Work out the mass equivalent of the energy packed into a magnetar's field, and near the surface it reaches tens of tons in every cubic centimeter. The field, holding no matter at all, weighs as much as a loaded truck crushed into the space of a sugar cube. The magnetism is not draped over the star as a weightless accessory. It is among the heaviest things present, dense enough to bend the space around it through its own gravity. That figure may even be a floor. The field we measure is the external one, the part that reaches into space and slows the spin. The field, buried in the interior, is thought to be stronger still, perhaps 10 times the surface value, locked away where we cannot read it directly. If so, the true reservoir runs larger than the visible field lets on, and the energy budget of a magnetar is deeper than its outward appearance suggests. This energy does not sit on the surface like static charge on a balloon. It threads the whole object, running through the crust and down into the core, and the lines of force are anything but slack. A magnetic field carries tension along its lines, resisting being stretched, and pressure across them, resisting being crushed, the way a thick bundle of stretched elastic both pulls along its length and shoves outward against whatever crowds it. Inside a magnetar, the field is not a tidy bar magnet shape. Much of it is believed to be wound into a twisted, knotted form buried in the interior, and a twist like that stores energy the way a wound rubber band does, with no release unless the winding is undone. The twist is also guarded by a conservation law. The total knottedness of a magnetic field, a quantity called its helicity, is very hard to remove, so the energy bound up in the winding cannot quietly bleed away even over long stretches of time. It has to be released, not dissolved. What keeps the winding from undoing itself is the crust. Below a thin outer skin, a neutron star's crust is a crystalline lattice of atomic nuclei, locked in a rigid, ordered structure, bathed in a sea of free electrons, growing denser and more neutron-rich with depth. By current estimates, it is the strongest material in the universe, able to bear stresses billions of times beyond what steel can take before it fails. Nothing on Earth comes close. It is also a near-perfect electrical conductor, and that detail is decisive because it means the magnetic field lines are effectively frozen into the crust. They cannot slip through the crystalline matter or rearrange on their own. Wherever the crust holds still, the field anchored in it must hold still as well. That is the latch on the entire system. The twisted interior field holds an enormous reserve of energy, and a smoother, lower energy arrangement exists that it does not occupy. Reaching that arrangement would require the field lines to move, and the field lines are locked into a crust that does not move. So the most energetic, stable object the universe can build short of a black hole sits in a higher energy state than it could in principle occupy, held there by nothing but the rigidity of a shell a mile or so thick. The energy is not draining away, it is pinned. It is not pinned perfectly. Over thousands of years, the buried field does slowly rearrange, migrating through the crust by processes with names like Hall drift and ambipolar diffusion, in which the field is carried along by drifting electrons or eased through the core by slow currents of matter. As the field shifts, it presses on the crust from within, and stress accumulates in the crystalline shell exactly the way strain builds along a geological fault as the plates beneath it grind. The crust deforms, bears the load, and holds. The field beneath keeps pressing. The stress keeps climbing. These processes run on a timescale of thousands of years, close to how long a magnetar stays violently active, so the slow loading of the crust and the length of the dangerous phase are very likely the same clock ticking. A magnetar differs from every ordinary neutron star in one decisive way. An ordinary neutron star has a strong field too, but not strong enough to load its crust anywhere near the breaking point, so that crust can hold for as long as the star exists. Only a magnetar's field generates internal stresses that rise into the same range as the crust's own breaking strength. The strongest material in the universe meets the one force able to rival it, and the two are set against each other inside a single object a dozen miles across. That contest, not the size and not the spin, is what makes a magnetar dangerous, and the crust does not yield like soft clay. It is brittle and rigid, so when it finally fails, it may not slip gently a little at a time, but fracture all at once, releasing what it held in a single stroke. A magnetar in this phase does almost nothing a casual glance would catch. It turns slowly, once every few seconds, giving off a faint, steady glow of X-rays, and to an instrument it looks like one more dead star adrift in the dark. What that stillness conceals is a system loaded to an extraordinary degree, a wound spring held shut, a fault strained toward its limit, carrying the energy of 1,000,000 years of sunlight behind a shell driven a little closer to failure with every passing century. The unsettling thing about a magnetar is not that it is loud, it is that it is silent, and the silence is not peace. It is the stillness of something fully loaded and not yet released. The way the most dangerous moment on a fault is not the earthquake itself, but the long quiet before it, when everything looks settled and the strain has nowhere left to go. A wound spring will not stay latched forever. A loaded fault will not hold without end. The energy of 1,000,000 years of sunlight is pinned behind a shell being driven, slowly and without pause, toward the moment it can hold no longer. The question is no longer how much energy is stored, or what keeps it in place. The question is what happens in the instant the crust finally gives. The crust reaches the limit of what it can bear, and it fractures. Not the way rock fractures on Earth. The crust of a magnetar is locked to the magnetic field threaded through it, every line of force anchored in the crystalline lattice as if welded there. So when a region of crust finally yields and shifts, even slightly, it drags the anchored field with it. The footpoints of the field lines lurch into new positions, and the vast external field, suddenly held at the wrong points, is forced to rearrange. Lines snap into new configurations and reconnect, and the field drops at last into the lower energy shape it could never reach while the crust held firm. The energy pinned for centuries is freed in a single convulsion. This is a starquake. Exactly how the failure unfolds is still debated, which is part of what keeps these objects at the front of research. In one picture, the crust cracks first, like a fault, and the moving crust shakes the field above it. In another, favored by much recent work, the trigger sits in the magnetosphere itself, where the twisted external field grows unstable and reconnects, and the crust is shaken from above rather than from below. Either way, the outcome is the same: a sudden reconnection of the field and a violent release of stored energy, but which end gives way first is not yet settled. The motion involved is almost nothing. The gravity at a magnetar's surface is so crushing that the crust cannot rise into anything we would call terrain. Its tallest features no more than millimeters high, and when it fails, the actual displacement may be less than the width of a hair. The energy does not come from the distance moved. It comes from the stress released. The crust is loaded to a pressure billions of times beyond steel across its entire volume, and even a slight relaxation of that pressure, spread through a shell a mile thick and miles wide, frees a staggering total. The largest earthquakes our planet can produce release roughly the energy of a power plant running for years, packed into a moment. A single large starquake can release, in a fraction of a second, around 1 billion times more than that, more than every earthquake in the entire history of the Earth combined, out of an object you could cross on foot in an afternoon. A crack finer than a hairline, on a shell a mile thick, freeing the output of the sun across thousands of years. That energy does not come out as sound because there is no air to carry it. It comes out as light and motion. Part of it floods the surface with sudden heat, igniting a burst of X-rays. Part of it accelerates particles to enormous speed along the field lines. Much of it travels as magnetic waves, called Alfvén waves, racing along the field and sloshing energy between the crust and the core. And part of it pours into the reconnecting field, which launches a trapped fireball of electrons, their antimatter twins, the positrons, and photons held captive on the closed loops of field just above the surface. The fireball cannot escape, because the field that made it also confines it. It can only remain and radiate, cooling slowly, pinned to the star. As the magnetar rotates, that glowing, trapped fireball swings toward us and away with every turn, brightening and dimming in time with the spin. This is the source of the pulsing tail in the light we receive, the steady beat once every few seconds in the fading glow after a flare. The rhythm in that 2004 signal, once every 7.5 seconds, was the trapped fire of a starquake sweeping past our line of sight as the broken star turned. The fracture does something else that we have actually measured. It sets the entire star vibrating. A neutron star struck hard enough rings, oscillating at specific frequencies fixed by its size, its structure, and the stiffness of its crust, the same way a struck bell sounds the particular tones set by its shape and its metal. After the giant flares of 1998 and 2004, X-ray telescopes caught exactly this in the decaying tails of the events. The brightness flickered not only with the slow spin but with faster, steady rhythms layered on top, oscillations repeating tens and even hundreds of times a second. Those rhythms were the vibration modes of the neutron star itself, the resonant tones of a dead star set, ringing by its own quake. The oscillations spanned a wide range, from a few tens of cycles a second up to several hundred, and some of the higher tones may involve the core, coupled to the crust through the magnetic field. Because the frequencies depend on the interior, on the thickness of the crust, and the state of the matter beneath it, reading those tones is a way to probe the inside of an object we can never cut open. A bell's tone reveals its shape and metal. The ringing of a magnetar revealed, in the same way, something of what it holds inside, in the tones it sounded after it cracked, 50,000 light-years away. The quake leaves one more mark. At the moment the crust shifts, the rotation of the whole star can jump, the spin rate stepping suddenly faster or slower as the crust resettles and pulls on the superfluid sea of neutrons in the interior. We see these abrupt changes in timing alongside the bursts, and they are direct evidence that the crust physically moved, that something solid and a mile thick lurched into a new position and changed how the entire object turns. Most of these failures are small. When a magnetar enters an active stretch, it can crackle with short bursts, each lasting a fraction of a second, each releasing roughly as much energy as the sun gives off in a year, sometimes dozens or hundreds of them over weeks as the crust adjusts a little at a time. In rare episodes, it can fire hundreds of short bursts in a matter of hours, a storm of cracking that often marks the start of an active phase. Larger fractures, rarer, release the sun's output over thousands of years in a single flare, and at the far end of the scale sit events of a wholly different order, where not a patch but a vast section of the crust gives way at once. Those are rare enough and violent enough to deserve their own reckoning. For a loaded magnetar, none of this is a possibility. It is a certainty. A shell strained year after year toward a breaking point it is being driven past cannot hold forever. It will crack. The only thing we cannot say is when, because nothing about the buildup is visible from outside until the failure has already happened, and the light that tells us it happened is the same light that carries the blow. There is no tremor before this earthquake, no foreshock to read across the galaxy. The first thing any distant observer learns of a starquake is the radiation arriving from one. The small cracks are routine, the ordinary background noise of a magnetar settling under its own field. But the crust does not only fail in patches. Once in a great while, a magnetar fails on the largest scale it is capable of, and the energy that escapes does not stay in its own neighborhood. It crosses the galaxy. So the question that closes the gap back to where this began is simple. What does the largest possible starquake look like? And what happens when its light finally reaches a world 50,000 light-years away? A starquake usually cracks a patch. Once in a long while, a magnetar fails almost everywhere at once. A giant flare is what happens when the fracture is not local but nearly global, when a vast section of the crust gives way together, or the entire twisted magnetosphere reconnects in a single stroke. Instead of releasing the energy of a year of sunlight, or a few thousand years of it, the star releases the sun's entire output across tens of thousands of years, and it does so in about 1/10 of a second. For that fraction of a second, a single dead object outshines the combined light of every star in its galaxy, hundreds of times over, almost all of it in gamma rays. What lets that energy reach across the galaxy rather than fading into its own neighborhood is the same field that stored it. When the field reconnects, it does not simply spill outward in every direction and dissipate. It traps much of the release in a dense fireball of radiation and matter held on its own closed loops, confining it and concentrating it. The field is both the bomb and the barrel. The brightness this produces is staggering past the point where ordinary physics would allow it. A giant flare shines hundreds of millions of times brighter than the level at which radiation pressure should blow the emitting gas apart, the limit that caps how bright normal objects can get. The only reason the plasma is not instantly scattered is that the magnetic field holds it in against the force of its own light. Nothing without a magnetar's field could contain a release like this. The field is what makes the flare possible, and the field is what aims it. A giant flare has a shape in time. It opens with a hard initial spike, 1/10 or 2 of a second long, which carries most of the energy and nearly all of the danger. A wall of gamma rays released almost instantaneously. Then comes a long tail, fading over several minutes, pulsing steadily at the rotation period of the star as the trapped fireball turns in and out of view. The spike is the rupture. The tail is the wreckage cooling, still pinned to the star, still pouring out radiation brighter than any ordinary sun for minutes after the crust has resettled. Events on this scale are extraordinarily rare. In roughly 60 years of watching the sky in gamma rays across a long succession of spacecraft, only 3 giant flares have ever been confirmed from magnetars in our galaxy and its near neighbors. 3. Each one rewrote part of what we understood, and the first arrived before anyone knew what a magnetar was. On the 5th of March, 1979, a wave of gamma radiation swept through the solar system, and saturated detectors on spacecraft scattered from Earth out past Venus. By timing its arrival across that spread of instruments, its source was traced to a supernova remnant in the Large Magellanic Cloud, a small companion galaxy about 160,000 light-years away. The burst rose in a few thousandths of a second and faded with an 8-second pulse, the unmistakable mark of a spinning neutron star. The remnant it came from was young, only a few thousand years old, an early hint that whatever produced the flare was a fresh remnant rather than an ancient one. At the time, nothing in physics readily explained how an object that size could produce a flash that bright from that far. The event sat unexplained for years, filed under a new label, soft gamma repeater, for sources that flung out irregular bursts of gamma rays. The idea that these were neutron stars carrying fields 1,000 times beyond the ordinary would not be proposed until more than a decade later. The 1979 flare was the first time we recorded a magnetar at full strength, before there was a word for what produced it. The second came on the 27th of August, 1998, from a magnetar inside our own galaxy, around 20,000 light-years away. Its radiation reached Earth on the night side of the planet and ionized the upper atmosphere anyway, stripping electrons from the air in the dark, where the sun could not be blamed. A dead star, 20,000 light-years off, changed the electrical state of our night sky for as long as the burst lasted. The third was the one we have already met, the flare of December 2004, and it stood alone. Its initial spike released roughly 100 times more energy than either of the two before it, the most powerful burst ever recorded from beyond the sun, 3 events in 60 years, and the strongest of them outweighed the other two combined. If a giant flare can be picked up clear across the Milky Way, then from a much greater distance it would look, for a fraction of a second, like one of the short, sharp gamma-ray bursts that telescopes catch from across the universe. A handful of those bursts have now been traced not to remote cosmic explosions, but to specific nearby galaxies, including the directions of Andromeda and the galaxy known as M81. One detected in 2020 was localized to a galaxy roughly 11 million light-years away, and its profile fit a magnetar giant flare better than anything else. If that reading holds, then some of the flashes we have collected for decades, taking them for the deaths of distant stars, are instead the crust failures of magnetars in other galaxies, the same starquakes we record at home, carried across millions of light-years. A giant flare may be a distinct hidden population inside the catalog of gamma-ray bursts, mistaken until recently for something grander and farther. The reach that began as a crack in a shell a mile thick extends not only across our galaxy, but between galaxies entirely. Most failures stay small for a clear reason. A short burst needs only a small patch of crust to slip, and that happens often. A giant flare needs the field to have wound itself into a large-scale twist that fails altogether, and a configuration that extreme builds rarely and reconnects rarely. The same object that crackles with minor bursts for years may produce one true giant flare in its entire active life, or none at all. The same physical event registers at 3 different scales, set only by how far away it is read. Up close, it would be instant destruction. Across the galaxy, it bends a planet's magnetic field and disturbs its atmosphere. Across intergalactic space, it arrives as a faint, brief flicker we very nearly filed under another name. One crack in one crust, read 3 ways. The only variable the distance between it and the instrument that caught it. We have followed the magnetar from the flash that reached us, through the field that powers it, down to the crust that holds and at last breaks. What we have not asked is where such a thing comes from. Nothing about an ordinary star suggests its remains could end up wound in the strongest field in the universe, loaded with the energy of 1,000,000 years of sunlight, and cracking hard enough to be seen between galaxies. So, the question that turns us back toward the beginning is this: what has to happen to a star for it to leave behind a magnetar? Start with the count, because the count is hard to believe. The Milky Way holds somewhere between 100 billion and 400 billion stars. Across all of it, and the small galaxies orbiting it, the number of magnetars ever confirmed is about 30. Not 30,000, not 30 million, 30. If you could tag every confirmed magnetar in the galaxy and scatter the tags at random, you could search a volume containing tens of billions of stars before finding one. By the raw census, a magnetar is among the rarest things the galaxy is known to contain. A magnetar is not, by its nature, a kind of star. It is a phase, a stretch of time in the life of a neutron star, and a brief one. A neutron star may drift through space for billions of years, but its magnetar phase, the span during which the field is strong enough and active enough to crack the crust and throw out flares, lasts only about 10,000 years. 10,000 years sounds long against a human life. Against the age of the star, it is nothing, a single percent of 1% of its existence. After that, the field weakens, the crust quiets, the bursts stop, and what remains is an ordinary silent neutron star, indistinguishable at a glance from the countless others. The 30 we have found are the 30 caught mid-tantrum in the narrow window when they are still loud enough to notice. So the 30 are not the whole population, they are only the ones currently active. Behind them, the galaxy is thought to hold an enormous number of dead magnetars, objects that passed through their violent phase long ago and have since gone cold and quiet. Their fields decayed, their crusts settled. Estimates run into the tens of millions. The sky is salted with the corpses of magnetars that have already finished, drifting unseen, betraying nothing. This is the first place the count misleads. It makes a magnetar sound like a freak, a 1 in 10 billion accident. In truth, the galaxy has made tens of millions of them. We see 30 only because we can see a magnetar at all for just the thin sliver of time while it is still erupting. The other direction the count misleads is in suggesting these objects are unimportant by their rarity. They are not. A magnetar is difficult to detect precisely because it is so small and so dark between outbursts. It is a sphere a dozen miles across, radiating little steady light, most of it in X-rays the atmosphere blocks, invisible to the eye and faint even to the instruments built to find it. The only times a magnetar announces itself are the bursts and flares, which come without schedule and pass in seconds. Much of what we know about them comes from catching those brief moments, which means our census is shaped less by how many magnetars exist than by how lucky our timing has been. A magnetar that has not flared in the few decades we have watched simply does not appear in the tally. The 30 are not a measurement of how many there are. They are a measurement of how many happened to shout while we were listening. What turns one in roughly 10 neutron stars into a magnetar rather than an ordinary one is the real question, and it does not have a settled answer. A magnetar needs a field 1,000 times beyond the neutron star norm, and the field has to come from somewhere. The leading idea is that it is generated in the first seconds of the neutron star's life, when conditions are violent enough to act as an engine, and that only neutron stars born a particular way cross the threshold into the magnetar range. A competing idea is that the strongest fields are simply inherited, passed down from progenitor stars that were already unusually magnetic before they died, the field surviving the collapse and concentrating as the core shrank. The two pictures are not entirely exclusive, and the honest position is that we do not yet know which dominates. What is clear is that the path is narrow. Most dying stars of the right mass leave behind a plain neutron star. Only a minority leave a magnetar, and the difference is decided in the moments around the star's death. There is one more clue in where they are found. The active magnetars we know sit in young settings, near clusters of massive stars, and inside fresh supernova remnants only thousands of years old. They are not scattered evenly among the ancient stars of the galaxy. They cluster where stars have died recently, which fits a picture in which the magnetar phase comes early and ends fast. By the time the surrounding remnant has faded, the magnetar has usually gone quiet too. The youth of their neighborhoods is another way of reading the brevity of their lives. Hold the shape of all this together. A magnetar is the brief, furious opening chapter of a neutron star's existence, lasting 10,000 years out of billions, produced by a minority of the right kind of stellar death, generating in its short, active life the strongest field in the universe and the flares that come with it, then falling silent for the rest of time. We have found 30. The galaxy has likely made tens of millions, and every one of them began the same way, in the death of a massive star. Which is where the origin has to start. A magnetar is not built from nothing. It is what is left when a particular kind of star runs out of the fuel that held it up. And to understand the object that reached across the galaxy to touch a planet, we have to go back to the ordinary process every massive star is already living through right now, the slow burning that keeps it standing, and the day that burning has to stop. What happens inside a star in the hours before it dies? A star is a standoff between two forces, and it lasts exactly as long as the fuel that holds the standoff in place. Gravity pulls every part of a star inward without pause, working to collapse all that mass toward the center. What resists it is pressure, generated by nuclear fusion in the core, where hydrogen fuses into helium and the reaction pours out energy. That energy pushes outward and holds the weight of the entire star up against its own gravity. The two are matched so finely that a star can keep the same shape for billions of years, neither collapsing nor flying apart. Our own sun has held that balance for more than 4 billion years and will hold it for billions more. Massive stars do not get billions of years. A star, born with more than about 8 times the mass of the sun, carries far more weight pressing inward, so its core must burn hotter and faster to make the pressure that holds it up. It burns through its hydrogen in a few million years rather than 10 billion. And when the hydrogen in the core runs low, the balance does not simply end, it shifts. The core, no longer fully supported, contracts under gravity and heats further, and at the higher temperature, it ignites the next fuel. Helium fuses into carbon and oxygen. When the helium is spent, the core contracts and heats again, and carbon ignites, fusing into neon and magnesium and sodium. Each time a fuel runs out, the core shrinks, grows hotter, and lights the next, heavier fuel in line. What turns one in roughly 10 neutron stars into a magnetar rather than an ordinary one is the real question, and it does not have a settled answer. A magnetar needs a field 1,000 times beyond the neutron star norm, and the field has to come from somewhere. The leading idea is that it is generated in the first seconds of the neutron star's life, when conditions are violent enough to act as an engine, and that only neutron stars born a particular way cross the threshold into the magnetar range. A competing idea is that the strongest fields are simply inherited, passed down from progenitor stars that were already unusually magnetic before they died, the field surviving the collapse and concentrating as the core shrank. The two pictures are not entirely exclusive, and the honest position is that we do not yet know which dominates. What is clear is that the path is narrow. Most dying stars of the right mass leave behind a plain neutron star. Only a minority leave a magnetar, and the difference is decided in the moments around the star's death. There is one more clue in where they are found. The active magnetars we know sit in young settings, near clusters of massive stars, and inside fresh supernova remnants only thousands of years old. They are not scattered evenly among the ancient stars of the galaxy. They cluster where stars have died recently, which fits a picture in which the magnetar phase comes early and ends fast. By the time the surrounding remnant has faded, the magnetar has usually gone quiet too. The youth of their neighborhoods is another way of reading the brevity of their lives. A magnetar is the brief, furious opening chapter of a neutron star's existence, lasting 10,000 years out of billions, produced by a minority of the right kind of stellar death, generating in its short active life the strongest field in the universe and the flares that come with it, then falling silent for the rest of time. We have found 30. The galaxy has likely made tens of millions, and every one of them began the same way, in the death of a massive star. Which is where the origin has to start. A magnetar is not built from nothing. It is what is left when a particular kind of star runs out of the fuel that held it up. And to understand the object that reached across the galaxy to touch a planet, we have to go back to the ordinary process every massive star is already living through right now, the slow burning that keeps it standing, and the day that burning has to stop. What happens inside a star in the hours before it dies? A star is a standoff between two forces, and it lasts exactly as long as the fuel that holds the standoff in place. Gravity pulls every part of a star inward without pause, working to collapse all that mass toward the center. What resists it is pressure, generated by nuclear fusion in the core, where hydrogen fuses into helium and the reaction pours out energy. That energy pushes outward and holds the weight of the entire star up against its own gravity. The two are matched so finely that a star can keep the same shape for billions of years, neither collapsing nor flying apart. Our own sun has held that balance for more than 4 billion years and will hold it for billions more. Massive stars do not get billions of years. A star born with more than about 8 times the mass of the sun carries far more weight pressing inward, so its core must burn hotter and faster to make the pressure that holds it up. It burns through its hydrogen in a few million years rather than 10 billion, and when the hydrogen in the core runs low, the balance does not simply end, it shifts. The core, no longer fully supported, contracts under gravity and heats further, and at the higher temperature it ignites the next fuel. Helium fuses into carbon and oxygen. When the helium is spent, the core contracts and heats again, and carbon ignites, fusing into neon and magnesium and sodium. Each time a fuel runs out, the core shrinks, grows hotter, and lights the next, heavier fuel in line. Everything is now in place for the fastest and most violent transformation in the life of any star. The core has reached the threshold. The pressure that held it for millions of years is gone. Gravity, pressing inward the entire time and at last meeting nothing to oppose it, is about to take the whole core down. So the question is what gravity actually does in the instant nothing stands against it. How does a core the size of a planet become a magnetar in less than a second? When the brace fails, the collapse takes less than a second. A moment before, the iron core is about the size of the Earth, holding more than the mass of the Sun. Then the support gives way, and the core falls inward on itself, not slowly. The inner core implodes at speeds approaching a quarter of the speed of light, tens of thousands of miles every second, folding a planet-sized object down toward a ball a dozen miles across in a fraction of a heartbeat. There is no comparable event in the ordinary universe. No process that takes something the size of a world and crushes it to the size of a city in less time than it takes to blink. What happens to the matter on the way down rewrites it completely. The pressure grows so extreme that electrons are driven into the protons inside the nuclei, and each merger turns a proton into a neutron and emits a neutrino. Across the whole core, this happens at once. The matter sheds its electrons and its protons together and converts itself into a dense fluid of neutrons. The atoms are gone, the vast empty gulf inside every atom. The space between a nucleus and its electrons that makes ordinary matter almost entirely void is gone with them. What remains is neutrons packed directly against neutrons, with nothing in between, the entire core becoming something close to a single colossal atomic nucleus. At that point, a new pressure appears, the one that finally stops the fall. Neutrons obey a quantum rule, the exclusion principle, which forbids any two of them from occupying the same state at once. Pack them tightly enough, and they resist being pushed closer, not from any ordinary force between them, but because the rule itself will not permit it. This neutron degeneracy pressure stiffens the core the instant it reaches the density of an atomic nucleus, and the collapse that nothing else could halt stops against a wall built out of a law of quantum mechanics. The density at that wall is almost beyond stating. A single teaspoon of this matter would weigh billions of tons on Earth, the mass of a mountain folded into the space of a sip. The whole core, more than the mass of the Sun, is now a sphere you could drive across in 20 minutes, made of the most concentrated, stable matter that exists. The inner core does not simply stop. It overshoots, compresses slightly past nuclear density, and being now almost incompressible, it rebounds, slamming outward into the outer core, still raining down onto it. That rebound launches a shock wave upward through the infalling star. And here the story reaches a problem physics has wrestled with for decades. By every straightforward calculation, that shock should stall. It loses energy, breaking apart the iron it plows through, and more energy to neutrinos streaming out of the dense core, and it grinds to a halt partway out, no longer able to push against the matter still falling inward. On paper, the star should fail to explode. In simulations, for many years, it did fail. The shock died, and the model star collapsed quietly into a black hole instead of blowing apart. What revives the shock is the flood of neutrinos. The newborn core is so hot, around 100 billion degrees, that it radiates neutrinos in numbers beyond imagining. For those first seconds, the matter is so dense that even neutrinos, the most weakly interacting particles there are, cannot pass freely. They are briefly trapped, leaking out over about 10 seconds rather than escaping at once, which is part of why the burst lasts as long as it does. Almost all of them slip through the surrounding layers untouched. But a tiny fraction, perhaps 1 in 100, are absorbed just behind the stalled shock, and that small fraction deposits enough energy to reheat the shock and drive it outward again. The explosion is not powered by the rebound alone. It is powered by neutrinos, by a sliver of a flood so vast that even its leftovers can tear a star apart. Making this work in detail still tests the field. The revival seems to depend on the matter churning and overturning in 3 dimensions, on turbulence and sloshing motions behind the shock that only appeared once simulations grew powerful enough to model the collapse in full. The basic picture holds, but the explosion of a massive star remains one of the harder unsolved problems in astrophysics. The scale of energy moving through this is hard to hold. In about 10 seconds, the collapse releases roughly 100 times more energy than the sun will radiate across its entire 10 billion year life. About 99% of it leaves as neutrinos, pouring out invisibly in the first seconds. Around 1% goes into the kinetic energy of the explosion, the part that tears the star apart, and a tiny sliver, 1/100%, comes out as light. The supernova that can briefly outshine a galaxy of hundreds of billions of stars is the faint leftover of this event. The real release, the overwhelming majority, is a pulse of neutrinos that passes through everything and is gone in moments. We know this is true because we have caught it once. In 1987, a star exploded in the Large Magellanic Cloud, about 168,000 light-years away. Hours before its light arrived, detectors deep underground on Earth registered about 24 neutrinos in a span of seconds, the only neutrinos ever caught from a supernova. 24 particles, out of a flood beyond counting. After a journey of 168,000 years, they arrived before the light because they escaped the collapsing core at once, while the light had to wait hours for the shock to reach the surface. For a few seconds in 1987, we did not observe the aftermath of a stellar collapse. We detected the collapse itself as it happened. The neutron star that collapse should have left behind stayed hidden in the wreckage for over 30 years, and only recently have astronomers found signs of it buried in the cooling dust, exactly where the neutrino said it would be. When the revived shock finally reaches the surface and breaks out, the star is torn apart from the inside. The outer layers are flung into space at thousands of miles per second, carrying the elements built up over the star's life, the oxygen and carbon and iron, scattering them across the galaxy as the raw material of new stars and worlds. For weeks, the wreckage outshines its entire galaxy. But the part that matters for this story is not the explosion, it is what stays behind. At the center, where the collapse stopped against that quantum wall, sits a new object. At first, it is larger and hotter, a puffy proto-neutron star, perhaps 50 kilometers across, which shrinks and cools over the following seconds as its trapped neutrinos drain away, settling toward a sphere about 20 kilometers across that holds 1.5 to 2 times the mass of the Sun. It is born at 100 billion degrees, and it is spinning. This is a neutron star, formed in the span of a second from the ruin of a giant. And in a small fraction of these births, under conditions we have not yet fully pinned down, the object that emerges carries the strongest magnetic field in the universe. It is the densest, hottest, most extreme object the collapse can leave standing, and it is far stranger up close than the bare facts admit. Its gravity bends light around itself. Its surface outweighs mountains in every spoonful, and it is turning, faster than anything its size has any right to turn. Why does a dead star, only seconds old, spin hundreds of times every second? A neutron star is small enough and heavy enough to bend its own light around itself. Begin with the density, because every other extreme follows from it. The collapse packed more than the mass of the sun into a sphere about 20 kilometers across, with the matter crushed to the density of an atomic nucleus all the way through. A single sugar cube of it would weigh about 1 billion tons. Scoop up a thimbleful and you would hold the mass of every human being on Earth several times over if anything could hold it, which nothing could. This is matter with the empty space pressed out of it, atoms crushed until only their nuclei remain, touching. It is the densest, stable form of matter the universe permits. One more notch of compression, one step further down, and there is no stable object left at all, only a black hole. Density this extreme produces gravity beyond comparison. At the surface, gravity is about 200 billion times stronger than on Earth. An object dropped from waist height would slam into the surface at more than 1,000 kilometers a second. A human being would not stand on a neutron star and would not merely be crushed in the ordinary sense. The gravity would flatten a body into a film of atoms across the surface faster than any nerve could register the fall. A person who weighs 150 pounds here would, in the instant before being destroyed, weigh something on the order of tens of trillions of pounds. That same gravity makes the surface almost impossible to leave. To escape the Earth, a rocket must reach about 7 miles a second. To escape a neutron star, an object would need to be moving at somewhere between 1/3 and 1/2 of the speed of light. The flip side of that binding is energy. When matter falls onto a neutron star from far away, it arrives at a fraction of light speed and releases a tremendous share of its mass as radiation, something like 10 or 20%. Nuclear fusion, the process that powers stars, converts less than 1% of mass into energy. Letting matter fall onto a neutron star is more than 10 times as efficient, which makes these objects, when they pull gas off a companion star, among the brightest steady sources of X-rays in the sky. The same gravity that would kill you is also one of the most efficient energy sources in the universe. Now the light itself. Gravity this strong does not only pull on matter, it bends the path of light, exactly as Einstein's theory of gravity requires, and near a neutron star the bending is severe. Rays that leave the surface heading away from you, around the side of the star, are curved back into your line of sight. The result is that you see more than half of the surface at once. Part of the far hemisphere, the side physically turned away, is lifted into view by the bending of its own light. A neutron star does not show you a flat disk the way a planet does. It shows you a swollen, wrapped-around image, the back of the star curling into the edges of the front. And for compact enough stars, the same spot on the surface can appear more than once, its light arriving by 2 different bent paths. A little more compact, and the effect would close completely. Neutron stars sit just outside the regime, where light can be bent all the way into a circle, the photon ring that surrounds a black hole. They come within a hair of being able to trap light in orbit around themselves. None of this is a thought experiment. It has been measured. A NASA X-ray telescope called NICER, mounted on the space station, watched the light from hot patches on a spinning neutron star's surface, and the shape of the light curve as those patches rotated in and out of view was distorted in exactly the way the bending of light predicts. By modeling that distortion, astronomers around 2019 mapped where the hot spots sat and measured the star's radius to within about 1 kilometer, reading the size of an object thousands of light years away from the way its gravity warps its own light. That measurement matters because the radius, set against the mass, reveals how stiff the matter inside is, and so begins to answer what neutron star material actually does at densities we can never reproduce. The bending of light has become a ruler. Gravity does one more thing to the light, harder to picture but just as real. As light climbs away from the surface, it loses energy fighting the pull, and that loss stretches it toward redder wavelengths. Light leaving a neutron star reaches us shifted, its colors dragged down by 20 or 30%. Bound into that same effect is a slowing of time. A clock resting on the surface would tick noticeably slower than a clock far away by a similar fraction. Time runs slow at the bottom of that gravity well, and the reddened light is the visible mark of it. The surface beneath all of this is stranger than any landscape. Gravity so strong allows almost no terrain. The tallest mountain, a neutron star, can support stands only millimeters high, because anything taller is pulled flat. Above the solid crust sits an atmosphere perhaps centimeters thick, a thin shell of plasma pinned down by the crushing pull. On a magnetar, where the field reshapes that surface matter into chains locked along the field lines, even this thin skin behaves like nothing found anywhere else. Below the crust, the strangeness deepens. The matter there is thought to arrange itself into shapes named half in jest, after pasta. Nuclei squeezed into long rods and flat sheets as the pressure climbs. The so-called nuclear pasta, believed to be among the strongest structures that exist. Deeper still flows a sea of neutrons with no friction at all, a superfluid, and at the center lies a core whose true state remains unknown, perhaps holding forms of matter found nowhere else. There is even a ceiling on how much mass a neutron star can carry, a little over 2 times the sun, and a star pushed past it has nothing left to hold it up and collapses the final step into a black hole. Everything described so far is true of an ordinary neutron star, the common kind that forms in most of these collapses. The billion-ton sugar cube, the crushing gravity, the bent and reddened light, the millimeter mountains, the pasta and the frictionless sea, all of it is the baseline. A magnetar is one of these objects with the strongest magnetic field in the universe laid over the top, every extreme already named, plus a field 1,000 times beyond the neutron star norm. The impossible gravity and the rapt light and the slowed time are only the stage. The field is what makes the object reach across the galaxy. And there is one feature shared by every neutron star, ordinary or magnetar, that the collapse alone does not obviously explain. It spins, not gently, the way a planet turns, but ferociously, the fastest of them hundreds of times every second, a city-sized object heavier than the sun turning so fast its surface moves at a real fraction of the speed of light. A dead star, only seconds old, has no engine and no fuel. So where does that spin come from? And how did we first catch a neutron star in the act of turning? The spin comes straight from the collapse, and the physics behind it is something you can watch a figure skater do. When a skater pulls in their arms during a spin, they speed up with no push at all, purely because their mass has moved closer to the axis. Spin is a conserved quantity. Concentrate the same rotation into a smaller radius, and the rate has to rise to keep the total fixed. It is the same rule that spins up a draining bathtub and a forming planet, applied here on a scale with no equal. The iron core that collapses is roughly the size of the Earth, turning slowly, perhaps once a month, the lazy rotation of a stellar interior. Then it falls inward and shrinks by a factor of around 500, from the width of a planet to the width of a city. Because the rate climbs with the square of that shrinkage, the rotation speeds up by something like 250,000 times. A turn that took a month at the start takes a fraction of a second at the end. The newborn neutron star emerges spinning tens or hundreds of times every second, having done nothing to earn that speed except fall inward on its own slow turn. The surface speed this produces strains belief. On a neutron star turning hundreds of times a second, the equator moves at a sizable fraction of the speed of light. An object heavier than the sun, 20 kilometers across, whirling fast enough that its surface nears light speed, should by every ordinary intuition fling itself apart. Nothing holds it together except the same crushing gravity that flattens its mountains to millimeters, and that gravity is just strong enough to keep even this contained. The spin and the gravity both sit at the edge of what matter can survive, braced against each other. We learned that neutron stars spin this way by accident, in one of the strangest discoveries in the history of astronomy. In 1967, a graduate student named Jocelyn Bell Burnell was working with a new radio telescope outside Cambridge, scanning the sky and recording the data on long rolls of chart paper by hand, hundreds of feet of it every day. Among the traces, she noticed a small recurring smudge, a bit of signal that behaved like neither the known sources nor any earthly interference. The clue that it came from the stars rather than from the ground was timing. The smudge returned about 4 minutes earlier each day, keeping pace not with the sun but with the rotation of the sky itself, which marked it as something fixed among the stars. Looking closer, she and her colleagues found a radio pulse arriving with astonishing regularity. Once every 1 1/3 seconds, steady enough to set a clock by. Nothing natural was known to flash with that kind of mechanical precision. For a short while, the idea was entertained, half in jest, that it might be a beacon from another civilization, and the source was labeled LGM1 for Little Green Men. The doubt dissolved when a second pulsing source turned up elsewhere in the sky. 2 alien beacons in the same week was far less likely than one new kind of natural object. They had found a pulsar, a spinning neutron star, and the precise beat was simply its rotation. The Nobel Prize that followed went to the project's senior scientist and not to Bell Burnell, an omission still argued over decades later, which she has met with more grace than most could manage. The reason a spinning neutron star pulses at all is geometry. It fires beams of radiation from its magnetic poles, and those poles are usually not aligned with the axis it spins around, the same way Earth's magnetic north does not sit at the geographic pole. As the star turns, the beams sweep around the sky like the beam of a lighthouse. If one of them crosses the Earth on each rotation, we catch a pulse, 1 flash per turn. The beat is not the star blinking on and off. It is a steady beam swinging past us again and again at the rate the star spins, and we see only the pulsars whose beams happen to point our way. That radiation has to be paid for, and the bill is drawn from the spin itself. An ordinary pulsar gradually slows as it shines, converting the energy of its rotation into the radiation it pours out, shedding a sliver of its spin with every turn. The Crab Nebula, the wreckage of a supernova that astronomers recorded in the year 1054, holds a pulsar at its center turning about 30 times a second, and the energy it loses as it slowly winds down is what lights the entire nebula around it. A glowing cloud light years across, powered by the breaking of one spinning corpse. The steadiness Bell Burnell first caught has become one of the most powerful tools in physics. The rotation of a pulsar is so stable that the best of them rival atomic clocks. In the 1970s, Russell Hulse and Joseph Taylor found 2 neutron stars orbiting each other, and the orbit was decaying by exactly the amount expected if the system were losing energy to gravitational waves, the first solid evidence those waves were real, drawn entirely from the timing of a pulsar, decades before any built detector caught a wave directly. The work continued. In 2023, astronomers watching arrays of these clocks across the sky reported the first signs of a low background hum of gravitational waves passing through the galaxy, detected not with a machine but by listening for the coordinated stutter in the ticking of dead stars. The most precise natural clocks in the universe are the remains of stars that have already died. The fastest known pulsars spin not hundreds but over 700 times every second, their surfaces moving at close to a quarter of the speed of light. They were not born that fast. They were spun up later, by pulling matter off a companion star, the infalling gas delivering rotation the way a jet of water spins a mill wheel. A neutron star's spin is not fixed at birth. It can be added to, and it can be lost. How fast a pulsar slows reveals something hidden, because the rate of the slowdown, set against the period, gives the strength of the magnetic field doing the braking. It is the same reading met earlier, the one that lets us weigh a magnetar's field from across the galaxy. The stronger the field, the harder the brake, and the spin does not always ease down smoothly. Now and then, A neutron star jumps suddenly faster in an instant, a glitch, as the frictionless superfluid in its interior dumps some of its rotation into the crust, a direct fingerprint of the strange fluid sealed inside. This is where the magnetar parts from the ordinary pulsar. By the time we observe one, it turns slowly, once every 2 to 12 seconds, its enormous field having braked it hard over a short life. But it was not born slow. Like every neutron star, it came into being spinning furiously, perhaps once every few thousandths of a second, near the very limit of how fast such an object can turn at all. For an ordinary neutron star, that birth spin simply fades. For a magnetar, the leading idea is that the birth spin did something first, in the opening seconds. While the newborn star was still molten and churning, it built the field. So the question that carries us into the heart of the mystery is this: what does a spin of 1,000 times a second do to a star in the seconds after it is born, that a slower birth never manages at all? The fast birth spin does not simply fade. For a few seconds it runs an engine, and that engine builds the field. The engine is a dynamo, the same process that makes the Earth's magnetic field scaled up past recognition. A dynamo works wherever an electrically conducting fluid moves. The motion of charged matter carries and stretches magnetic field lines, and under the right conditions, the motion reinforces the field instead of tangling it away, so a weak seed field is amplified into a strong, ordered one. In the Earth, liquid iron circulating in the outer core does this slowly, over thousands of years, producing the half-Gauss field that turns a compass. A newborn neutron star runs the same principle at a violence the Earth could never reach, and it converts the raw energy of its own motion into magnetic energy as it goes. To see why, look at the object in its first seconds. It is not yet the rigid, settled star it will become. It is a proto-neutron star, born at around 100 billion degrees, still swollen and molten, with a scorching core and a cooler outer layer. That temperature difference, together with the outward seepage of trapped neutrinos, drives ferocious convection. Hot, neutron-rich fluid rises, cooler fluid sinks, and the whole interior overturns violently, churning like a pot boiling so hard the water leaps, except the pot is heavier than the sun, and each overturn takes 1,000th of a second. This fluid is a superb electrical conductor, threaded with currents, so every churning motion drags magnetic field lines along with it. Convection on its own would only make a chaotic tangle of small fields that cancel as often as they add. What turns that chaos into a single colossal field is rotation. If the newborn star spins fast enough, the spin twists the rising and sinking currents into a consistent direction, through the same sideways deflection that organizes storms on Earth, the Coriolis effect. The convection stops being random. It takes on a uniform sense of twist, and a twisting conductor is exactly what amplifies and orders a magnetic field rather than scrambling it. The faster the spin runs relative to the churning, the more efficiently the dynamo works. In 1992, two physicists, Robert Duncan and Christopher Thompson, worked out where the line falls. The dynamo reaches full strength only when the star is born, spinning at a particular rate, with a rotation period close to a single thousandth of a second, comparable to the time the convection takes to overturn. When the spin and the churning run on the same timescale, the two lock together. The dynamo hits peak efficiency, and the field is driven to around a quadrillion Gauss, 1,000 times beyond an ordinary neutron star, with the buried interior field likely stronger still. If the star is born spinning more slowly, even tens of times a second, which by any other measure is fast, the dynamo is feeble. The rotation and the convection never couple tightly. The amplification falls short, and the result is an ordinary neutron star near 1 trillion Gauss, strong but unremarkable for its kind. The gap between the most magnetic object in the universe and a routine neutron star is decided by how fast the core happens to be turning in the first instance, and the window that produces a magnetar is narrow. The whole process is over almost as soon as it begins. The amplification runs in the first 10 to 30 seconds, while the proto-neutron star is still hot enough to convect. After that, the star cools. The neutrinos finish draining away. The churning slows and stops, and the crust begins to harden. Whatever field the dynamo managed to raise in those few seconds is then frozen into the now rigid star, locked in place for the rest of its existence. A field that will shape the object for hundreds of thousands of years is set in less time than it takes to read this paragraph. Then the field acts back on the spin that produced it. A field that strong is a tremendous brake. It radiates energy and drags against everything around the star, and it drains away the very rotation that created it. The millisecond spin that ran the dynamo is gone within years to decades, slowed to the leisurely 2 to 12 seconds we measure when we finally observe a magnetar. The fast spin built the field, and the field then erased the fast spin. By the time we see one, the engine has long since shut down, the evidence of its furious birth wiped clean, leaving only the enormous field it produced and a slow turn that gives no sign of how fast the star once spun. That drained spin energy does not always vanish quietly. A neutron star born turning 1,000 times a second holds an enormous reserve of rotational energy, comparable to the energy of the supernova that made it. If a young magnetar sheds that spin quickly enough, the energy can pour into the still expanding debris of the explosion and light it from within. This is the leading explanation for the most luminous supernovae ever recorded, blasts that outshine ordinary ones by 10 or 100 times, and possibly for some of the long gamma-ray bursts as well. The same birth spin that forges the field can, in the right case, turn the explosion itself into one of the brightest events in the universe. This also explains why magnetars are rare, the 1 in 10 figure from before. To build one by dynamo, the star must be born spinning near that millisecond limit, and that requires the collapsing core to carry a great deal of rotation. Most massive stars do not deliver it. Across their lives, their cores shed angular momentum, braked by their own winds and their own weaker fields, so that by the time they collapse, the core turns too slowly to drive a strong dynamo. Only the uncommon star that holds onto enough spin all the way to the end produces a proto-neutron star fast enough to make a magnetar. The rarity of magnetars is, in part, the rarity of a fast-spinning death. There is an honest complication, and it is where the research now lives. The dynamo is the leading idea, but it may not be the only road. Some of the strongest fields might be inherited rather than built. When a stellar core collapses, it shrinks by a factor of around 500, and any field threaded through it is compressed with the matter, its strength rising by roughly 250,000 times simply because the same field lines are forced through a far smaller area. A progenitor that was already unusually magnetic, carrying a strong field at its surface and far more in its core, could reach magnetar strength through compression alone, with no dynamo at all. The two pictures are not exclusive, and recent work has given the inherited field route real support. Astronomers have found massive, strongly magnetic stars, at least one apparently the merged remnant of two stars, whose fields and masses point toward a magnetar at the end of their lives. Whether magnetars are mostly forged at birth by a dynamo, mostly inherited from magnetic progenitors, or some blend of both, is not yet settled, and it is one of the live questions keeping these objects at the front of stellar physics. What every version shares is the strangeness of what we are reconstructing. The field we measure today was set in a handful of seconds, in the convulsing interior of a star that died long ago and far away, and we read those vanished seconds backward from a slow-turning remnant and the energy it occasionally throws off. The most extreme magnetism in the universe is the fossil of an event that lasted less than half a minute and finished before there was anyone here to wonder about it. We now know what a magnetar is, how it is born, and how its impossible field is made. What we have not done is stand near one and look. If you could somehow survive at a safe distance and turn toward a magnetar, what would you actually see? The first surprise is that you would see almost nothing. The deadliest object in the galaxy is, to human eyes, very nearly invisible. A magnetar is about 20 kilometers across, so from any real distance, it is an unresolved point, a single dot of light, if it registers at all. And most of what it radiates is not light your eyes can use. Its surface burns at a few million degrees, far hotter than the roughly 6,000 degrees of the sun's surface. And an object that hot pours out its energy overwhelmingly in X-rays, a form of light no eye can detect. The thin sliver that falls in the visible range would look faintly blue-white, but it is such a small fraction of the total, and the star is so tiny that you could be staring straight at the most extreme object in the universe and see only a dim speck or nothing. A surface hotter than the sun, on an object more violent than almost anything in existence, would still look fainter than an ordinary star to a human at a survivable distance. The danger of a magnetar is not in how it looks. This is also why they stayed hidden from us for so long. We could not find magnetars until we built telescopes that fly above the atmosphere and see in X-rays and gamma rays. Because at the wavelengths the human eye and ground-based optical astronomy were built around, these objects barely register at all. They were invisible until we learned to look in the light they actually emit. That glow comes from a source unique to these objects. An ordinary pulsar shines by bleeding off its spin. A magnetar turns far too slowly to account for how brightly it burns in X-rays, and the explanation is that it is lit by its own magnetism. The colossal field, slowly decaying and rearranging within the crust, deposits heat continuously into the star, and that heat leaks out as the steady X-ray glow we detect between outbursts. It is the one class of star powered, in effect, by the decay of a magnetic field, shining on the slow ruin of the very field that defines it. Suppose, though, that you could approach close enough to resolve it as more than a point and survive the attempt, which you could not. The view would not obey ordinary optics. The gravity is strong enough to bend the star's own light around itself, so the disk would appear swollen, larger than its true size, with parts of the hidden far side curved into view around the edges. You would see more of the sphere than should be geometrically possible. The back of it folded into the rim of the front, and a bright patch on the surface could even appear in two places at once, as its light reached you by two separate bent paths. The surface beneath that warped image would be strangely smooth. The crushing gravity allows no real terrain, only features millimeters high, and on a magnetar the field locks the surface matter into chains aligned with the field lines, so what you would be looking at is not rock or metal in any familiar sense, but a condensed, field-ordered material that exists in no laboratory. The stars behind it would not sit still either. Their light, passing close to the magnetar on its way to you, would be bent aside, so the background field would appear smeared and shifted, distant stars dragged into short arcs and nudged from their true positions, a moving distortion in the sky wherever the magnetar drifted in front of them. Closer still, the strangeness would stop being gravitational and turn quantum. The space immediately around the star is filled with a field strong enough to alter the behavior of the vacuum itself. Light crossing that region would split according to its polarization, the two components traveling at slightly different speeds along slightly different paths. The image would shear and double and shimmer, as though you were viewing the star through a flawed crystal, except the crystal would be empty space, made birefringent by the field, with no surface for the distortion to belong to. The field around the star would not be empty. The twisted field lines arching out of the surface and looping back are threaded with charged particles, currents running along them, plasma trapped on the closed loops, and this whole structure glows in X-rays. To an instrument tuned to see it, the magnetar would not be a bare sphere, but a sphere wrapped in luminous, shifting arcs of field, brightest where the currents run strongest. That structure is enormous compared to the star. The magnetic domain, controlled by a slowly turning magnetar, reaches out hundreds of thousands of kilometers, so the visible object would be a tiny point buried at the center of a vast, glowing magnetic architecture. The field, not the surface, would be the most visible thing about it. Pull back to take in the setting, and the contrast would be stark. A magnetar in its active phase is young, only thousands of years past the supernova that made it, so it usually sits inside the expanding wreckage of that explosion, a faint glowing shell of debris light years across, often near the cluster of massive stars it was born among. Some magnetars do not stay put. The supernova that creates a neutron star can deliver a violent, lopsided kick, flinging it through the galaxy at hundreds of kilometers a second. So a few are found racing away from the cloud that bore them. The lethal point at the center would be nearly lost inside a soft, enormous cloud, the smallest and deadliest thing in the scene, wrapped in the largest and gentlest. And none of it would hold still, because the star turns. Every few seconds it completes a rotation, and the hot regions near its magnetic poles swing in and out of view, so the brightness would rise and fall in a slow, steady beat. If the magnetar were active, that rhythm would break without warning into bursts, sudden flares of X-rays and gamma rays as the crust shifted, each one brighter in an instant than the steady glow of years, and arriving, as always, in the same moment as the light that announced it. The object would not be a fixed lamp. It would be a slowly pulsing source prone to violent, unannounced flashes. No one will ever actually see a magnetar the way I have just described it, because there is nowhere to stand where the view and survival overlap. Anywhere close enough to resolve the swollen disk, the warped star field, the sheared light, the glowing arcs of field, you would already be dead, dissolved by the radiation and the field long before the image could form on a retina. The detailed portrait of a magnetar is entirely a reconstruction, assembled from physics and from light gathered at enormous range, a picture of something no eye will ever safely witness. We can calculate precisely how it would look, and we know with certainty that looking is impossible. The most vivid image we will ever have of a magnetar is one drawn entirely by inference. Which forces the real question. If you cannot survive close enough to see a magnetar clearly, then what, exactly, is doing the killing? What does that field and that radiation do to a body? And at what distance does each of them reach you? A magnetar does not kill in one way. It kills in several. And which method reaches you is decided entirely by how far away you stand. The reason is a difference in how two things weaken with distance. The magnetic field is a fixed property of the star, and a field like this falls off steeply with the cube of the distance. Move twice as far, and it drops not to a quarter but to an eighth. Move 10 times as far and it drops by 1,000. Radiation from a flare behaves differently. Light spreads out to fill a growing sphere, so its intensity falls with the square of the distance, more gently. Move twice as far and it drops to a quarter, not an eighth. So the two weapons have completely different reach. The field, for all its staggering strength, is a short-range threat that fades fast. The radiation, carried on a flare with the energy of 100,000 years of sunlight, fades slowly and crosses the galaxy. The danger of a magnetar is not one zone but a set of nested shells, each ruled by a different mechanism. Begin at the closest shell, within about 1,000 kilometers of the surface. Here the field still measures in the billions of Gauss, past the threshold where magnetism overwhelms the forces that hold an atom in its ordinary shape. At this range, the field does not burn you and does not crush you. It unmakes you chemically. Every molecule in your body is held together by electrons arranged in particular orbitals, and the shapes of those orbitals are what let atoms bond. The field deforms them, squeezing the electron clouds into needles aligned with the field lines, and the bonds that depend on the old shapes fail. Proteins unfold. The structures that organize your atoms into something alive come apart. The matter remains, but the chemistry of life stops, switched off by a force acting directly on the electrons inside you. This is destruction with no equivalent anywhere else. A fire leaves ash. A black hole stretches you. A magnetar at close range would leave your atoms whole and end you by making the molecules they form impossible. Because the field drops as the cube of distance, this shell is small. 1,000 kilometers is nothing on the scale of space, less than the width of many countries. But the field does not simply vanish past it. There is a wider zone, out to tens of thousands of kilometers, where the field is far too weak to threaten a body yet still strong enough to ruin any machine, inducing currents that would overwhelm electronics and fry a spacecraft's systems long before it reached the crew. Even out at 100,000 kilometers, where the field could not move a compass needle, it could still erase the magnetic strip on a credit card. The field is the most powerful force in the known universe and also one of the most local. Its lethal reach ends almost before interstellar distances begin. The next shell is set not by the field, but by the flare, and it reaches vastly farther, out to something like 10 light years. At that range, a giant flare delivers, in a fraction of a second, a dose of radiation large enough to kill. The lethal whole-body dose for a human is around 4 or 5 sieverts. A medical scan delivers a few thousandths of that. A giant flare at 10 light years would deliver several sieverts to anything unshielded on the daylit side of a planet, 1,000 times a medical scan, all at once. The gamma rays would pass straight through walls and bodies, ionizing atoms, breaking the bonds in living tissue, shredding the DNA in every cell. And it would be silent. Gamma rays trigger no sensation, so there would be no flash, no heat, no sound, no warning of any kind, because the radiation and the light that would tell you it had happened are the same thing, arriving together. You would feel nothing as the dose landed, and only days later would the body begin to fail. A planet's own magnetic field, which deflects ordinary particles, offers almost no defense against radiation this energetic. It is a solar flare amplified millions of times. Farther out, to a few hundred light years, the flare can no longer deliver a killing dose directly, but it can still end a world by a slower route. The gamma rays striking the top of an atmosphere drive chemical reactions that destroy ozone, the thin layer of molecules that shields a planet's surface from its own sun's ultraviolet light. A strong enough flare could strip away much of that ozone in a single stroke, and ozone reforms only over years. During those years, the planet's own star becomes the threat. Its ultraviolet light, normally absorbed high in the atmosphere, would reach the surface unfiltered, damaging the simplest links at the base of the food chain, the plankton and plants that everything else depends on. The magnetar would not need to touch the surface. It would only need to remove the shield and let the planet's own ultraviolet light do the rest. This is the same kind of mechanism proposed for nearby stellar explosions and tied by some researchers to a mass extinction on Earth hundreds of millions of years ago. There is one more variable beyond distance, and it cuts both ways. A giant flare is not perfectly even in all directions. The trapped fireball and the twisted field channel some of the output into preferred directions, so the same flare can strike harder along one line and softer along another. A planet might sit at a lethal distance and be partly spared by facing the wrong way, or sit farther out and be caught in the brunt of the beam. Distance sets the shell. Orientation decides where in the shell the real edge of danger falls. Beyond a few hundred light years, into the thousands, the effects become measurable rather than dangerous. This is the shell our planet actually occupies with respect to real magnetars. The flare of 2004, from 50,000 light-years away, compressed our magnetosphere and stirred our ionosphere and harmed no one. A flare from a few thousand light-years would do more. A stronger atmospheric disturbance, perhaps a slight, temporary thinning of ozone, but still fall short of catastrophe. The killing zones all lie closer in. Set the shells side by side, and the structure is clear. Within 1,000 kilometers, the field dissolves matter directly. Within tens of thousands, it destroys machines. Within 10 light years, the flare's radiation delivers a lethal dose. Within a few hundred, it strips the ozone and lets the local sunlight finish the work. Within thousands, it leaves a mark on the instruments and nothing more. One object, several different ways of causing harm, each running on a different mechanism with a different reach, the field falling as the cube and the radiation as the square, so the close shells belong to the field and the far ones to the light. There is real comfort in the arithmetic. The nearest magnetars we know of sit thousands of light years away, deep in the outermost shell, the one where even a giant flare would only register on instruments. The lethal zones, the shell of dissolved matter and the shell of fatal radiation are tiny against the distances between stars. Space is mostly empty, and the odds of a planet lying inside the killing range of a magnetar at the moment it erupts are extraordinarily small. We are not in that range. None of the ones we know of could reach us. All of this is why people reach for the comparison, why a magnetar gets called more dangerous than a black hole. It has more ways to harm, and some of them cross light years, but that comparison hides as much as it reveals. How does the danger of a black hole actually differ from this? Not in degree, but in kind. The honest answer is that a magnetar is more terrifying than a black hole in one narrow sense, and less by almost every other measure. Give the black hole its due first, because by most of the ways we rank extremity, it wins outright. A black hole is the deepest distortion of space-time that exists, a region where gravity has folded so steeply that not even light can climb back out. It has an event horizon, a one-way boundary past which nothing returns, a feature no other object in the universe possesses. It is, for all practical purposes, permanent. A magnetar's violent life lasts about 10,000 years before the field fades and the star falls silent. A black hole, left alone, persists for a span so long it makes the present age of the universe look like an instant, evaporating only over timescales carrying more zeros than the mind can hold. By depth of gravity, by permanence, by sheer extremity of physics, the black hole is the more extreme object, and it is not close. The popular picture of how a black hole threatens is wrong in a way that matters here. A black hole does not reach out and draw things in from afar with some special hunger. Gravity is gravity. A black hole of a given mass pulls on you exactly as hard as an ordinary star of the same mass would at the same distance, no more. If the sun were replaced this instant by a black hole of equal mass, the Earth would not be pulled in. It would continue in precisely the same orbit, colder, but undisturbed in its motion. The danger of a black hole is local, concentrated close to the horizon, where the gravity gradient turns severe. The killing mechanism there is tidal. Gravity pulls harder on the near side of an object than the far side, and close to a stellar black hole that difference grows so large across the length of a human body that it stretches the body lengthwise and squeezes it sideways, the effect often called spaghettification. There is a wrinkle worth noting, because it runs against intuition. The larger the black hole, the gentler the tides at its horizon, since the gravity changes more gradually across a wider boundary. Near a small stellar black hole, you would be torn apart well before reaching the horizon. Near a supermassive one, you could cross the horizon intact, feeling almost nothing at the moment of no return. So a black hole's danger is bounded. You have to go to it. Outside its narrow lethal zone, it behaves like any mass of its size, pulling but not projecting, and that is the sense in which it is passive. But even that is too clean. A black hole that is feeding is among the most ferociously active things in the universe. Matter spiraling into a large one heats and radiates with a brilliance that can outshine an entire galaxy of stars steadily for millions of years, and many launch jets of particles at nearly light speed that stab thousands of light years into space, able to sterilize whole regions around them. They are violent in motion as well. When two black holes spiral together and merge, they radiate several times the mass of the sun as pure gravitational waves in a fraction of a second, And for that instant, the collision shines in those waves more brightly than every star in the observable universe combined. We have caught those waves directly since 2015, and we have even photographed the shadow of a black hole against the glow of its own swirling gas. A quiet black hole waits. A feeding or colliding one is an engine of destruction at the scale of galaxies. Now the magnetar side, the narrow sense in which the word terrifying is earned. A black hole, quiet or feeding, sits in one place, and its danger is a property of how close you are. A magnetar projects harm by several independent mechanisms, and during a giant flare, it throws lethal radiation across light years to a planet that never moved toward it. It does this without warning, in a fraction of a second, by a process the victim need not understand or even know exists, and by more than one method depending on range, the field at close quarters, the radiation farther out, the ruin of an atmosphere farther still. The magnetar's danger is not a property of where you are. It is a property of when it erupts and whether you happen to lie along its path. That is a genuinely different kind of threat, and it is the real content behind calling it more terrifying. Hold the two side by side honestly, though, and the word terrifying has to be pried apart from the word powerful. The magnetar wins on immediacy, on stealth, on harm delivered per second. The black hole wins on nearly everything else, on total energy, on the depth of its physics, on permanence, on the scale of devastation. A feeding one sustains across cosmic time. A magnetar's furious phase is a brief flare in the life of a star, 10,000 years out of billions, and the active ones number only about 30 in the whole galaxy. A black hole, once formed, is effectively forever. And there are perhaps 100 million stellar black holes in our galaxy alone, with a giant one of 4 million solar masses anchored at its center. In any reckoning of raw power and endurance, the black hole is the greater object by a wide margin. The two are not even strangers, they are siblings from the same process. A dying massive star leaves a neutron star, sometimes a magnetar, if its collapsing core stays below a certain mass, and a black hole if it crosses it, a little more mass at the end, and the same death that builds a magnetar builds a black hole instead. They are two outcomes of one event, divided by a threshold of about 2 solar masses. The real distinction between their dangers is not which is stronger, but what kind of danger each is. A black hole is a hazard of place. It threatens you by where you are, and you stay safe by keeping your distance, which across the emptiness of space is nearly automatic. A magnetar is a hazard of time and alignment. It threatens you by when it breaks and whether you sit in its line, and no amount of keeping still protects you if you happen to be close enough when the crust gives. One danger is a location you can avoid. The other is a moment you cannot predict. That is why the two provoke such different unease. We make our peace with dangers we can steer around. We are far less easy with a danger that arrives on its own schedule, from a source we cannot see, by a mechanism that gives no signal until it has already struck. A black hole at least announces itself, by the glow of its feeding and the bending of light around it. A quiet magnetar gives nothing away until it erupts. The magnetar is not the more powerful object. It is the one that behaves least like a place and most like an event. None of this changes the practical reality, which is the same for both. Their killing zones are minute against the distances between stars. No black hole and no magnetar known to us sits anywhere near close enough to harm the Earth, and the chance of either reaching us in any human lifetime is vanishingly small. The comparison is a way of understanding two kinds of extremity, not a warning about either. Which leaves the question building quietly under all of this. If neither of these objects can touch us, if the nearest magnetar lies thousands of light years away and harmless, then why should any of it matter to a person lying in the dark, with nothing extreme anywhere near? The reassurance is real, and it is built from two things we rarely think of as protective: distance and time. Begin with time, because it does more work than it seems. a magnetar's dangerous life is brief. The phase in which the field is strong enough and active enough to crack the crust and throw out flares lasts only about 10,000 years, set by the slow drift of the field through the crust, the same gradual rearrangement that builds the stress until it gives. Against the billions of years a neutron star drifts through space afterward, that active window is a flicker, a fraction of 1% of the object's existence. The consequence is quiet but powerful. At any given moment, almost every magnetar that has ever formed is already dead. The galaxy holds perhaps tens of millions of them, and the overwhelming majority have long since cooled, their fields decayed, their crusts settled, drifting silent and harmless through the dark, the ones still capable of a giant flare, the ones that could, in principle, harm anything, number only a few dozen. The universe produces these objects often, but their dangerous phase is short, so the dangerous ones are always a vanishing fraction of the whole. Now distance, which does the rest. The nearest magnetars we know of lie several thousand light-years away. Set that against the killing zones from earlier. The shell in which a giant flare delivers a lethal dose reaches out about 10 light-years. The shell in which it can strip an atmosphere's ozone reaches a few hundred. The nearest active magnetar sits thousands of light-years beyond even that outer shell, far outside any range where it could do real harm. And distance is not a passive gap. It is an active shield, because radiation thins with the square of how far it travels. A giant flare from the nearest magnetar, crossing several thousand light-years, would reach us diluted by a factor of hundreds of thousands compared to its lethal range. It might be 100 times stronger than the flare of 2004 that compressed our magnetosphere and harmed no one, and it would still fall far below any level that could threaten life on the surface. The emptiness between us and them spreads every dangerous thing thinner the farther it has to come. We have already watched this play out. In 2020, a magnetar in our own galaxy, many thousands of light-years off, threw out a burst that included the first fast radio burst ever traced to a source inside the Milky Way, tying these stars to one of the genuine mysteries of modern astronomy, the brief, brilliant radio flashes that arrive from across the cosmos. It was an event of real violence at its source. Here, it passed through without the faintest threat to anyone, recorded by instruments and felt by nothing. A magnetar erupted in our galaxy within living memory, and the distance reduced it to data. The geography of the galaxy adds another layer of safety. Magnetars are born where massive stars form and die quickly, in dense, crowded stellar nurseries, mostly along the bright spiral arms and toward the busy center. The Sun does not live in such a place. It sits in a relatively empty stretch between the spiral arms, inside a large, low-density cavity that ancient supernovae cleared out over the last several million years, with the nearest young stars strung along the far wall of that bubble, hundreds of light-years off. We are not in a stellar nursery. We are not near the galactic center. The places that breed magnetars are almost all thousands of light-years from here, and the few objects that have drifted closer are old and quiet. Even counting every star within 10 light-years of the Sun, barely more than a dozen, not one is a neutron star, let alone a magnetar. Our corner of the galaxy is, by the standards of these dangers, about as safe as a corner can be. The strongest reassurance is written into the history of the Earth itself. Our planet has existed for about 4.5 billion years, and life has been present for most of it, through 5 great mass extinctions and countless smaller ones. Not one of those extinctions has ever been firmly traced to a magnetar, or to any blast of radiation from space. There is a single intriguing candidate, a die-off more than 400 million years ago, that some researchers have tentatively linked to a burst of gamma rays from a nearby stellar catastrophe, but the case remains unproven and argued over, a maybe rather than a fact. Across 4.5 billion years, in a galaxy full of these objects, the worst that can honestly be said is that a radiation strike from space might possibly have contributed to one extinction once, and even that is uncertain. The risk is small enough that life on Earth has come through the entire span of its existence without a confirmed instance of it. The two things that keep us safe are the same two things that can make the universe feel desolate. The vast, cold distances between stars, the emptiness that makes space seem lonely and indifferent, are exactly what dilute every flare and every field to nothing before they reach us. And the brevity of these violent lives, the fact that nothing in the cosmos stays at its most extreme for long, is what keeps the dangerous ones rare at any single moment. The emptiness is the shield. The impermanence is the shield. The features of the universe that can seem the bleakest, its enormous distances and the way it holds nothing still, are turned around here into the very things that protect a small, warm world tucked into a quiet stretch of an ordinary galaxy. So the magnetars are out there, real, every bit as violent as the physics says. Their fields 1,000 times beyond any other object, their crusts loaded and waiting to break. But they are far, and they are mostly already dead, and the ones still burning are scattered across distances that drain their fury to a whisper long before it could ever reach here. The night sky is safe to look at. There is nothing overhead that is going to fall. If these objects cannot touch us, if they are too far and too brief to matter to our safety, then the only question left is whether they matter to us in some other way. Is there any real connection between that distant, ancient violence and the body lying here in the dark, or are they simply strangers we happen to be able to see? There is a connection, and it is not a poetic one. It is exact. The same physical process that built the Magnetar's lethal field is running beneath your feet right now, and it is keeping you alive. Recall what makes a magnetic field. In the end, not magnets, but motion. A field is generated whenever an electrically conducting fluid moves, and above all, when it moves and rotates at once, because the motion drags the field lines along, and the rotation organizes that dragging into a coherent, self-sustaining whole. This is the dynamo. In the newborn magnetar, it ran at an unthinkable pitch, a churning sea of nuclear matter spinning 1,000 times a second, amplifying the field to a quadrillion Gauss in a handful of seconds. The same principle, the very same physics, is at work inside the Earth. About 3,000 kilometers beneath the surface, below the rock of the mantle, the Earth's outer core is a vast ocean of liquid iron, hotter than the surface of the sun. We know it is liquid because earthquakes send waves through the planet, and the way those waves bend and stop reveals a molten layer wrapped around a solid inner core at the center. That iron ocean is not still. Heat rising from below, and the slow freezing of the inner core, which grows by about 1 millimeter a year and releases both warmth and lighter elements as it solidifies, keep the iron churning in great convective currents. The whole thing turns once a day with the planet, and the rotation bends those currents through the same Coriolis effect that shaped the convection in the newborn neutron star. A rotating, convecting, conducting fluid. That is a dynamo, and it generates the Earth's magnetic field, the half-Gauss field that has turned compasses for as long as there have been compasses. That field works for you every moment of your life. It reaches beyond the atmosphere and forms a magnetic shield around the whole planet, deflecting the constant stream of charged particles off the sun and much of the cosmic radiation drifting in from deep space. Without it, that radiation would strike the upper atmosphere directly, stripping it away over time and reaching the surface in far greater quantity. You have very likely seen this shield at work. The aurora, the curtains of green and red light near the poles, is the visible sign of it. The moment when particles from the sun are funneled down the field lines and crash into the upper atmosphere, lighting it up. That quiet glow in a northern sky is the same shield, made visible, that a magnetar's flare compressed from 50,000 light-years away in the event this whole story began with. The thing the distant monster reached out and dented is the thing that paints the auroras and keeps the air on this world. You can see what the loss of such a dynamo means by looking at Mars. Mars once had a churning, conducting core and a magnetic field of its own, still written into the magnetism frozen in its oldest crust. Then, around 4 billion years ago, its smaller core cooled too far, the convection slowed, and the dynamo shut down. The field faded. And once the shield was gone, the solar wind had open access to the Martian air and stripped much of it away into space over the following ages, leaving the thin, cold atmosphere and the dry surface we find today. A planet's ability to hold on to its air, and perhaps its ability to hold on to life, can hinge on whether a sea of metal is still moving in its core. The Earth's dynamo is still turning. Mars lost the same machine we still run, and the gulf between the two worlds is, in large part, the gulf between a dynamo that kept going and one that stopped. So the same mechanism builds both the deadliest field in the universe and the gentle shield over your head, and the only difference is the setting. The Magnetar's dynamo was fast, fed by a millisecond spin and a sea of nuclear matter, and it produced a field 2,000 trillion times stronger than the Earth's. Violent enough to crack the star and reach across the galaxy, then burned out in a geological instant. The Earth's dynamo is slow, weak, and patient, producing a field you cannot feel, running quietly for billions of years with billions more to go. The same physics stretched across 15 factors of 10, the same span as the ladder of fields from earlier. Same equation. Wildly different numbers. One outcome destroys, the other protects. The dynamo is not rare. It is one of the most common processes in the universe. It runs in the sun, where moving plasma generates the field that drives the 11-year cycle of sunspots, and the flares our own field then deflects. It runs in Jupiter, which carries the strongest planetary field in the solar system. It runs, in slow and tangled form, across the whole galaxy, threading the space between the stars with faint magnetism. Magnetism born from motion is everywhere, on every scale, from the iron beneath your feet to the plasma of stars to the gas of entire galaxies. The magnetar is not a freak intrusion into an otherwise orderly cosmos. It is the most extreme expression of a process that is also, in its quiet form, the reason this planet is livable at all. The same family of physics, running at one extreme, makes the most dangerous object known. Running at another, it makes a home. And the Earth's version is not frozen or finished. The field shifts and wanders. It has weakened measurably, even over the last 2 centuries, and has grown thin in places, and over the long reaches of time it does something stranger still. Every few 100,000 years, on no fixed schedule, the entire field reverses, north and south trading places, the last full reversal having happened around 780,000 years ago. We can read that history directly in the rocks of the sea floor, which recorded the direction of the field as they hardened, laying down stripe after stripe of flipped and reflipped magnetism on either side of the ridges where new crust is born. The dynamo under your feet is a living, changing thing, turning and drifting and now and then reversing. And at this moment in its long history, it is simply doing its quiet work, holding the shield in place while you lie here. The connection, then, is real, and it runs deep. The magnetar and the Earth are not strangers separated by an unbridgeable gulf. They are 2 settings of one physical process, the distant violence and the nearby protection written in the same law. But the kinship goes deeper than the dynamo. The magnetar was born in the death of a massive star, in a supernova that forged the heavy elements and scattered them across space, and that origin reaches into your body more literally than any analogy. What part of the magnetar's beginning is actually inside you, right now, as you breathe in the dark? The part of the magnetar's beginning that is inside you is the matter itself. The iron moving through your blood was forged in the death of a star. in the same kind of death that leaves a magnetar behind. To see how literal that is, go back to the very beginning. The Big Bang produced almost nothing that you are made of. It made hydrogen and helium and the barest trace of the next lightest element, and then it was over. No carbon, no oxygen, no nitrogen, no iron, none of the atoms that build a living body. For the first stretch of cosmic history, the universe was a thin fog of the two lightest gases and nothing more. Every heavier atom that exists, every one in your hands and your bones and your blood, was manufactured later, inside stars. And yet the Big Bang did leave something in you. The hydrogen in every molecule of water in your body, 2 atoms in each, is primordial, made in the first minutes of the universe and never altered since. The lightest part of you is the oldest matter there is, nearly 14 billion years old, and it has been inside countless stars and clouds before it arrived here. The elements that make life possible were built by the same fusion that holds a star up. Deep in stellar cores, hydrogen is fused step by step into heavier elements, and among them are carbon, oxygen, and nitrogen, the backbone of every molecule biology uses. The carbon in every cell, the oxygen you are breathing as you lie here, the nitrogen woven through your proteins, the calcium hardening your bones, the phosphorus threaded along your DNA, were all assembled in stars that lived and died before the sun was born. You are not made of earthly material that happens to be old. You are made of stellar ash. Iron is the clearest case because its story is so exact. The iron in your body, about 4 grams of it, most of it riding inside the hemoglobin of your red blood cells, was forged in the final stages of massive stars and in the supernovae that end them, both the kind that collapse into neutron stars and the kind where a white dwarf detonates. Every iron atom in you was made in one of those deaths and flung across space, drifting for ages before it became part of a planet and then part of you. And iron is not a passive passenger. It is the atom hemoglobin uses to grip oxygen in your lungs and carry it to every tissue. Each breath you take works because an iron atom, made in a dying star, binds the oxygen and ferries it through you. The most basic act of staying alive runs on metal forged in stellar fire. The heaviest elements have a stranger origin still, and it leads straight back to the objects in this story. Fusion in a star can build elements only up to iron, because past iron, as we saw, fusing costs energy rather than releasing it. So the elements heavier than iron cannot be made the ordinary way. They are built by capturing neutrons. Some of it happens slowly, inside aging stars, layer by layer over thousands of years, producing elements like barium and lead. But the heaviest and rarest, the gold, the platinum, the iodine, the uranium, are built in a rapid version of the process that needs an environment dense with free neutrons and more violent than anything fusion offers. For decades, it was unclear where in the universe such a place existed. The answer, confirmed only recently, is among the most fitting in all of science. In 2017, 2 neutron stars, the same kind of dead star this whole story has circled, spiraled together and merged. And for the first time, we caught the collision in both gravitational waves and light, the 2 signals arriving within seconds of each other after a journey of 130 million years. In the glow that followed, astronomers read the spectral fingerprints of heavy elements being forged in the wreckage, gold and platinum and more, an amount of gold many times the mass of the Earth, made in a single collision of neutron stars. So the heaviest atoms you carry were very likely made by the very kind of object at the center of this story. The iodine your thyroid needs, the trace metals your enzymes depend on, were probably born in the collision or the violent death of neutron stars, the near cousins of magnetars, and there is growing evidence that the most magnetic, fastest spinning of these deaths, the kind that can leave a magnetar, may forge these elements as well. The gold in a ring on a finger and the iodine in a gland in your neck trace back, in all likelihood, to the same family of objects whose most extreme members reach across the galaxy to crack and flare. Hold the timeline of it, because the timeline is the quiet marvel. None of these atoms were made for you, or near you, or recently. The hydrogen came from the first minutes of the universe. The carbon and oxygen and iron came from stars that died before the sun existed, scattering their ash into a vast cloud. The gold and the heavy trace metals came from the collisions of stellar corpses. And 4.5 billion years ago, an enriched cloud carrying all of it collapsed to form the sun, the planets, and eventually the material that became living things. Your body is not the leftover of a single star. It is an anthology of cosmic history, primordial gas and stellar fire, and the wreckage of neutron stars, gathered into one warm, breathing form. And the link closes cleanly on the magnetar. The supernova that leaves a magnetar behind is the same explosion that forges and flings the heavy elements outward, so the birth of a magnetar is also an act of creation, seeding the galaxy with the very atoms that build worlds and bodies. The event that produces the most dangerous object in the universe is, in the same instant, one of the events that makes life chemically possible. The destroyer and the maker are not two different deaths. They are one. The magnetar is not an alien horror set apart from you. It is a relative, made by the same kind of stellar death that assembled the iron in your blood and the lystic gen in your breath, standing on the far violent side of a process whose gentle products are lying here in the dark, breathing. So, as you lie here, with iron forged in a dead star moving through your veins, a dynamo of liquid metal turning slowly beneath you, and the whole long story of these objects laid out from the flash that opened it to the matter that ties them to you, there is one thing left to settle. After all of it, what is the single thought to carry down into sleep? The single thought is this: everything in the story you have just heard is also here, in this room, in your own body, in a gentler form, and that is the whole of the comfort. Begin with what is moving in you right now. In every red blood cell you carry, about 1 billion atoms of iron sit cradled in hemoglobin, and you hold something like 25 trillion of those cells. Every one of those iron atoms was forged in the death of a star, in the kind of supernova that can leave a magnetar behind, and scattered across space long before the Earth existed. Trace the path of a single one of them. Made in the last day of a dying star, flung out in the explosion, adrift in a cold cloud for billions of years, folded into the gas that became the sun and its planets, locked into the rock of a young Earth, drawn up through soil and root and the food you have eaten, carried into your marrow, and set at last inside a cell that is this moment, binding oxygen and ferrying it to your slowing heart. A journey of billions of years, ending quietly in your bloodstream tonight. And the body does not waste it. As old cells break down, the iron is salvaged and used again. The same ancient atoms passed from cell to cell for the whole of your life. The fire that built the most dangerous object in the universe also built the metal carrying the breath into you as you lie here. Take a breath now, and notice what it actually is. The oxygen you draw in was forged in stars, and the iron that seizes it inside you was forged in stars. So each breath is a meeting of two kinds of stellar ash, doing together the simplest work there is, keeping you alive. The act of breathing is stellar chemistry, carried out in the dark, without effort, all night long. Beneath you, far below the floor, the dynamo is turning. The ocean of liquid iron in the Earth's core is moving as it has for billions of years, and out of that slow motion comes the magnetic field that wraps the whole planet. That field is over you now, reaching far past the atmosphere, turning aside the wind of particles from the sun and much of the radiation from deep space. The same shield a magnetar once pressed inward from across the galaxy, doing its silent work above you while you lie still. It is the same kind of dynamo that built the magnetar's lethal field, running here in its gentlest setting, its only effect on your night to keep you safe without your ever feeling it. Above that field is the night sky, and you can look at it without any fear at all. Somewhere among those points of light, scattered through the dark, are the magnetars. Most are long since gone quiet, cooled and silent. Their violence finished ages ago. The few still burning lie thousands of light years away, far beyond any distance from which they could reach you, their fury drained to nothing by the emptiness it would have to cross. There is nothing overhead that is going to fall. The distance is the mercy, and the distance is vast, and you are resting safely underneath all of it. The magnetar shines. When it shines, in X-rays and gamma rays, the most violent light there is. You also shine. Your warm body gives off light constantly, a soft infrared glow of about 100 watts, the gentlest end of the very same spectrum the magnetar hurls across the galaxy. You are, in the harmless way, a faint, warm star of your own, glowing quietly into the room. The difference between the deadliest object in the universe and the warmth of your own skin in the dark is not a difference of kind. It is only a difference of degree along one unbroken scale of light. Even the rhythms rhyme. The magnetar in that first story turned once every 7.5 seconds, and we received that beat written in gamma rays, the spin of a dead star reaching us across 50,000 years. Your heart beats about once a second, moving the star-forged iron quietly through you, a rhythm of the same universe, on the gentle side of it, here, now, in the warm dark. So hold the whole of it together, lightly, as you drift. The iron in your blood, made in a dying star. The dynamo beneath you, turning out the shield overhead. The far magnetars, ancient and distant and harmless, the faint warm light your own body gives off into the room. Every piece of this, the violence and the protection and the matter and the safety, is written in the same handful of physical laws, and you are lying on the gentle side of all of them. The most terrifying object in the galaxy turned out not to be a stranger. It is a relative, born of the same deaths that made you, shaped by the same dynamo that shields you, shining in the same light you give off yourself. What is it worth to know that the fiercest light in the sky and the warmth in your own chest are the same physics, only kinder here? That is the thought to carry down. Not that the universe is dangerous, though in its far reaches it is, but that the same forces that make it dangerous are the ones that made you and hold you safe, and that the gulf between you and the violence is so wide and so kind that you can close your eyes beneath it without a single worry tonight. Thank you for spending this quiet hour here, for staying curious in the dark instead of turning away from it. There is something rare in choosing to spend a stretch of night thinking carefully through something real, and I am glad to have done it with you. The iron is in your blood. The shield is in place. The magnetars are far away and long gone still. Let your breathing slow, let the day go, and rest well, knowing you are made of the same fire that lights the galaxy, lying safe in the gentlest corner of it. Good night.